Welcome to Dark Cosmos Theory. Before we begin this journey into one of the most profound questions ever asked about our universe, I want to ask you to do something. Hit that like button if you find this exploration fascinating, subscribe to stay connected with more cosmic mysteries, and drop a comment telling me where in the world you're watching from. Your engagement helps us reach more curious minds across the planet. Now, let's dive into something that might fundamentally change how you see reality itself. There is a pattern in the darkness that shouldn't exist. Deep in the computational laboratories of the European Southern Observatory, a team of astrophysicists noticed something strange while analyzing gravitational lensing data from distant galaxy clusters. The data came from the Dark Energy Survey, a massive project mapping hundreds of millions of galaxies across a significant portion of the observable universe. What they found wasn't dramatic in the way explosions or collisions are dramatic. It was subtle, a deviation so slight that it almost disappeared into statistical noise. But it was consistent, repeating across multiple datasets, refusing to vanish no matter how many times they recalculated. Dark matter, the invisible substance that makes up roughly 85% of all matter in the universe, was behaving in a way that didn't quite match predictions. The researchers expected to see random distributions following the mathematical patterns of cold dark matter theory, the framework that has dominated cosmology for decades. Instead, they observed correlations. Clusters of dark matter appeared to be responding to each other across distances where no known force should create such coordination. The gravitational influence was too subtle, the distances too vast, the timing too precise. Picture the cosmic web, that magnificent structure of dark matter filaments connecting galaxy clusters across billions of light years. Now, imagine discovering that the vibrations traveling through this web aren't random. They pulse with rhythms that suggest coordination rather than chaos, like neurons firing in patterns that carry information rather than noise. This is what the data implied, though no one said it explicitly in the published papers. The language remained cautious, buried in phrases like unexpected correlation coefficients and deviations from lambda CDM predictions. Scientists working with the illustrious simulation, one of the most comprehensive computer models of cosmic structure formation, tried to recreate the pattern. They adjusted parameters, modified initial conditions, introduced new variables representing exotic physics. Nothing produced the exact signature appearing in the observations. The standard model of cosmology, which has successfully explained phenomena from the cosmic microwave background to galaxy rotation curves, couldn't account for this particular anomaly. It was as if the universe contained an additional organizing principle, something operating on scales too large for our theories to capture. The researchers published their findings in the monthly notices of the Royal Astronomical Society, careful to frame everything as preliminary results requiring further investigation. But in the footnotes and appendices, in the careful language of academic restraint, they acknowledged something unsettling. If the correlations were real and not some unidentified systematic error in the measurements, then dark matter possessed properties beyond what current physics describes. Properties that might allow information transfer across cosmic distances. Properties that could, in principle, support complexity and organization on scales dwarfing anything previously imagined. Other anomalies began surfacing as more data accumulated. The Hubble Space Telescope detected unexpected alignments in how dark matter halos surrounded galaxies. These invisible cocoons of gravitational influence showed orientations that correlated across megaparsecs, millions of light years of seemingly empty space. Random chance should produce no such pattern. Gravity alone couldn't explain the coordination. Dark matter particles, if that's truly what they are, don't interact with each other or with normal matter except through gravity. They should pass through each other like ghosts, forming structures only through the patient accumulation of gravitational attraction over billions of years. Yet here was evidence suggesting something more. The alignments persisted across cosmic epochs, traced backward through redshift measurements, showing that these correlations existed when the universe was half its current age. This wasn't a recent development or a local anomaly. It appeared to be a fundamental feature of how dark matter organizes itself on the largest scales. Some researchers privately began using a different vocabulary in their conversations, though rarely in their papers. They spoke of dark matter behaving less like dead material responding passively to gravity, and more like a medium capable of maintaining coherent structures across space and time. The implications hovering behind these observations remained largely unspoken in official channels. Science proceeds through careful steps, through reproducible measurements and peer review. But the anomaly was there, documented in multiple independent datasets, resistant to conventional explanations. Dark matter, the substance comprising most of the universe's mass, the invisible scaffolding upon which galaxies form and cluster, appeared to possess an additional layer of organization that our theories had never predicted and our measurements had never before been sensitive enough to detect. And this was just the beginning of what would emerge as we looked deeper, as our instruments grew more sophisticated, as we accumulated more observations of this vast invisible realm that surrounds and permeates everything we can see. The anomaly was a to be, crack in our understanding, a small fissure that would widen into questions about the very nature of the cosmos, and whether the universe itself might be something far stranger than a collection of matter and energy, evolving according to impersonal physical laws. Chapter 2. What dark matter really is. Before we can understand what makes dark matter strange, we need to understand what makes it normal, or at least as normal as invisible matter, comprising most of the universe, can be. Dark matter's existence was first seriously proposed in the 1930s by Swiss astronomer Fritz Zwicky, who noticed something peculiar about the Coma cluster, a massive collection of galaxies hundreds of millions of light years from Earth. The galaxies in this cluster were moving too fast. He measured their velocities through Doppler shifts in their spectral lines and calculated how much mass would be needed to keep them gravitationally bound together. The visible matter, all the stars and gas he could detect, provided only a fraction of the required mass. Either Newton's laws of gravity failed on cosmic scales, or most of the mass was invisible. Zwicky called this missing component dunkle materie, dark matter, and suggested it might comprise most of the universe's mass. For decades, the idea remained controversial, a curiosity at the margins of mainstream astronomy. Then, in the 1972, Vera Rubin and Kent Ford conducted detailed observations of galaxy rotation curves, measuring how fast stars orbit at different distances from galactic centers. According to Newton's laws and Einstein's general relativity, stars farther from the galactic center should orbit more slowly, just as outer planets in our solar system move more leisurely than inner planets. But that's not what Rubin and Ford observed. Stars at the outer edges of spiral galaxies move just as fast as those closer to the center, as if they were being pulled by far more mass than the visible stars and gas could provide. The rotation curve problem appeared in galaxy after galaxy. No matter which spiral galaxy they examined, the same pattern emerged. The visible matter couldn't account for the observed velocities. Either our understanding of gravity was fundamentally wrong on galactic scales, or galaxies were embedded in massive halos of invisible matter extending far beyond the visible disk. The dark matter hypothesis provided the simplest explanation. If galaxies sat within much larger spheres of invisible material, the gravitational field would remain strong at large distances, naturally explaining the flat rotation curves. Gravitational lensing provided independent confirmation. Einstein's general relativity predicts that massive objects bend space-time, causing light from distant sources to curve around them like water flowing around a rock. Astronomers can measure this lensing effect by observing how background galaxies appear distorted when viewed through massive galaxy clusters in the foreground. By mapping these distortions, they can calculate the total mass of the lensing cluster, including both visible and invisible components. The results consistently show that visible matter accounts for only about 15% of the total mass. The remaining 85% is dark, detectable only through its gravitational influence. The cosmic microwave background, that faint afterglow of the Big Bang filling all of space, provides yet another line of evidence. The CMB contains tiny temperature fluctuations, regions slightly hotter or cooler than average, imprinted when the universe was 380,000 years old. These fluctuations represent density variations in the primordial plasma, seeds that would eventually grow into galaxies and galaxy clusters. But the pattern of these fluctuations only makes sense if dark matter was present in the early universe, providing additional gravitational pull that enhanced the growth of structure. Sophisticated analysis of CMB data from satellites like WMAP and Planck yields precise measurements of dark matter's abundance. About 27% of the universe's total energy density, compared to just 5% for normal matter. Simulations of cosmic structure formation provide the most comprehensive validation of dark matter theory. Cosmologists use supercomputers to model how the universe evolved from the nearly smooth conditions of the CMB era to the rich structure we observe today. These simulations start with the initial conditions measured in the CMB and apply the laws of gravity and gas dynamics to see what structures emerge. When the simulations include dark matter in the proportions indicated by observations, they reproduce the cosmic web, the distribution of galaxies, the abundance of galaxy clusters, and numerous other features, matching the real universe with remarkable fidelity. Without dark matter, the simulations produce universes that look nothing like ours. So, what is this substance that dominates the universe's matter content yet remains invisible to telescopes? Despite its abundance and gravitational importance, dark matter has never been directly detected. We know what it isn't more clearly than what it is. It isn't normal atomic matter, because the abundance of light elements produced in the Big Bang, which depends sensitively on the density of protons and neutrons, rules out enough baryonic matter to account for dark matter. It isn't neutrinos because these particles move too fast to clump into the dense concentrations observed in galaxy halos. It isn't black holes or other compact objects made of normal matter because such objects would produce observable gravitational lensing effects on background stars, and multiple survey projects have shown that not enough of these objects exist. The leading candidate remains weakly interacting massive particles, WIMPs, hypothetical particles that interact only through gravity and possibly the weak nuclear force. WIMPs would be produced in the Big Bang, would move slowly enough to clump into dark matter halos, and would remain stable enough to persist through the universe's current age. Massive underground detectors have searched for rare events where a WIMP collides with an atomic nucleus, but despite decades of increasingly sensitive experiments, no conclusive detection has been made. Other possibilities include axions, extremely light particles proposed to solve certain problems in quantum field theory, or sterile neutrinos, hypothetical cousins of ordinary neutrinos with different interaction properties. What we do know is that dark matter forms a cosmic web, a network of filaments connecting galaxy clusters across the universe. Galaxies form where these filaments intersect, drawn together by the gravitational pull of dark matter concentrations. The web structure emerges naturally from gravitational instability, the same process that causes dense regions to grow denser over time as their stronger gravity pulls in more material. Computer simulations show that this process, starting from the tiny density variations in the CMB, inevitably produces a web-like structure matching observations. This is the accepted picture of dark matter, the framework that has dominated cosmology for the past several decades. It is a picture of passive material, responding to gravity, forming structures through slow gravitational aggregation, providing the scaffolding for galaxy formation, but otherwise playing no active role in cosmic evolution. Dark matter in this view is gravitationally important but otherwise inert, a substrate upon which the interesting physics of stars, planets, and life can unfold. But what if this picture, successful as it has been at explaining observations, captures only the surface behavior of something far more complex? What if dark matter's apparent simplicity is the result of our inability to measure its other properties rather than an inherent lack of such properties? The anomalies beginning to emerge in the data might be the first hints that dark matter is stranger, more active, more organized than standard cosmology assumes. And that possibility leads to questions that push the boundaries of physics into territory that sounds more like philosophy or even science fiction, yet might be the next frontier of serious scientific investigation. Chapter 3. The Behavior Problem. Physics is built on predictability. Given the state of a system and the laws governing its evolution, you should be able to calculate what happens next. This determinism breaks down in quantum mechanics, where probability replaces certainty, but even quantum systems obey statistical laws that allow precise predictions about aggregate behavior. Dark matter, as currently understood, should follow these principles. It should behave like a collection of particles responding to gravitational forces according to well-defined equations. Most of the time, it does exactly that, but sometimes it doesn't. The first hints of the behavior problem appeared in observations of galaxy collisions. When two galaxies crash together, their stars pass by each other like two swarms of insects, rarely colliding because the distances between stars are enormous compared to stellar diameters. Normal matter gas clouds don't pass through so cleanly. Gas atoms collide, generating friction and heat that causes the gas to lag behind the stars. Dark matter, which doesn't interact electromagnetically, should behave like the stars, passing through essentially unimpeded. In most collisions, that's exactly what happens. The bullet cluster, a famous example, shows dark matter halos passing right through each other while the gas slows down, providing some of the clearest evidence for dark matter's existence. But in other collisions, dark matter doesn't behave as expected. In some systems, dark matter appears to lag slightly behind where it should be, as if experiencing drag even though it shouldn't interact with anything. In others, the dark matter distribution shows asymmetries that computer simulations struggle to reproduce. The discrepancies are subtle, often within the uncertainties of measurement, but they appear consistently enough that several research groups have begun publishing papers noting these anomalies. Proposals for self-interacting dark matter, where dark matter particles scatter off each other through some unknown force, can explain some observations but create problems elsewhere. No single modification to dark matter physics accounts for all the anomalous behaviors. Dwarf galaxies present another puzzle. These small satellites, orbiting larger galaxies like the Milky Way, should be dominated by dark matter, making them excellent laboratories for studying dark matter properties. Standard cold dark matter theory predicts that dwarf galaxy halos should have dense central concentrations, cusps in the density profile that get steeper toward the center. But observations show that many dwarf galaxies have cores, central regions, where the density stays relatively flat. The discrepancy, known as the core cusp problem, has persisted for over 2 decades, despite extensive theoretical efforts to resolve it. More puzzling still is the missing satellites problem. Cold, dark matter simulations predict that halos, the mass of the Milky Way, should contain hundreds or even thousands of smaller subhalos, each potentially able to form a dwarf galaxy. But we observe only about 60 satellite galaxies around the Milky Way, far fewer than predicted. Various explanations have been proposed, such as feedback from star formation, preventing gas from cooling in small halos, but none fully resolve the discrepancy. It's possible that most small dark matter halos exist but remain dark, never forming stars and therefore remaining undetectable. Or it's possible that dark matter doesn't clump on small scales the way cold dark matter theory predicts, suggesting additional physics that suppresses small-scale structure formation. Then there's the timing problem. When cosmologists run simulations of galaxy formation, they need to fine-tune the rates of various processes like gas cooling, star formation, and supernova feedback to reproduce the observed properties of galaxies. The required timing is suspiciously precise. Star formation needs to turn on at just the right epoch, proceeding at just the right rate, shutting down at just the right time in just the right places. Too much star formation produces galaxies with too many stars. Too little leaves galaxies dimmer than observed. The Goldilocks precision required for the simulations to match observations suggests either remarkable coincidence or missing physics that naturally produces the observed timing. What makes these problems particularly interesting is that they manifest as both excess predictability and excess chaos. In some contexts, dark matter behaves more uniformly than it should, showing correlations across larger scales than random fluctuations would produce. In other contexts, it shows more variation than expected, with individual systems deviating from predicted properties. This combination of too much order and too much disorder doesn't fit the profile of measurement error, which would randomly push observations in all directions. It fits the profile of a system governed by additional organizing principles beyond the simple gravitational attraction of non-interacting particles. Consider the velocity dispersion profiles of galaxy clusters, which measure how fast galaxies move relative to the cluster's center of mass at different distances from that center. Cold dark matter theory makes specific predictions about these profiles based on how dark matter halos form through gravitational collapse and merger. Most clusters match the predictions reasonably well, but a subset show velocity dispersions that are either too low or too high, and these outliers aren't randomly distributed across parameter space. They cluster together in particular ranges of mass and redshift, suggesting a systematic effect rather than random scatter. Gravitational lensing measurements provide another example. The detailed shapes of lensing distortions around galaxy clusters depend on the three-dimensional distribution of dark matter along the line of sight. Most measurements match theoretical expectations, but a statistically significant fraction show peculiarities that computer simulations don't reproduce. These include unexpected alignments between different lensing clusters in the same region of sky, or lensing strength that varies with position in ways that simple dark matter halo models can't explain. Again, the anomalies are subtle, but they appear in multiple independent surveys using different instruments and analysis techniques. The behavior problem extends to dark matter's role in cosmic structure formation itself. Observations of the galaxy distribution on the largest scales, using surveys that map millions of galaxies across billions of light-years, reveal patterns in the cosmic web that contain more information than the initial density fluctuations measured in the CMB should produce. It's as if some additional process has amplified structure beyond what pure gravitational growth from CMB-measured initial conditions should yield. Several exotic physics scenarios have been proposed to explain this, including interactions between dark matter and dark energy, or modifications to gravity on cosmic scales. But each explanation creates its own problems, and none has gained widespread acceptance. What if the behavior problem exists because we're trying to understand an active, responsive medium using theories developed for passive, inert matter? What if dark matter doesn't just respond to gravitational forces, but also to information flowing through the cosmic web, creating feedback loops and correlations that simple particle physics can't capture? This would mean dark matter possesses properties beyond mass and gravity, properties that allow it to organize itself in ways that look sometimes random and sometimes coordinated, depending on context and scale. The question hanging over all these observations is whether we're seeing the signatures of new particle physics, new gravitational physics, or something else entirely. New particle physics would mean dark matter particles interact with each other, or with other fields, in ways we haven't detected yet. New gravitational physics would mean general relativity breaks down on cosmic scales in ways that mimic dark matter behavior. But there's a third possibility. one that most physicists haven't seriously considered because it sounds too strange and challenges too many assumptions. What if the behavior problem exists because dark matter is not just matter, but also the substrate of something alive, something organizing itself according to principles that transcend particle physics and emerge only when observing the system at cosmic scales? Before dismissing this possibility as pseudoscience or speculation, we need to understand just how precisely the cosmic web resembles the networks that define living systems here on Earth. Chapter 4. The Cosmic Web. As a nervous system, the human brain contains roughly 86 billion neurons, each one connected to thousands of others through a dense network of synapses. Information flows through this network in patterns of electrical and chemical signals, creating the emergent phenomenon we call consciousness. Now consider the cosmic web, that vast structure of dark matter filaments connecting galaxy clusters across the observable universe. The similarities are striking enough that cosmologists working on visualization projects routinely face the challenge of distinguishing images of brain tissue from images of cosmic structure. The resemblance is not superficial. Let's start with the numbers. The observable universe contains approximately 2 trillion galaxies, each one a concentration of matter within the cosmic web's structure. Galaxy clusters, where many galaxies congregate, function as nodes in the network, connected by filaments of dark matter and gas stretching across tens or hundreds of millions of light years. Between these filaments lie vast voids, regions of space containing very little matter, forming the empty spaces in the web. This architecture, nodes connected by filaments with empty spaces between, defines both neural networks and cosmic structure. The fractal dimension provides a mathematical way to compare these structures. Fractal dimension measures how completely a structure fills space at different scales. A perfectly straight line has dimension 1, a completely filled plane has dimension 2, a completely filled volume has dimension 3. Real complex networks fall somewhere between, showing similar patterns when you zoom in or out. The cosmic web has a fractal dimension around 2.5, meaning it fills space less completely than a solid but more completely than a random scatter of points. Neural networks in the brain have fractal dimensions in a very similar range, between 2.3 and 2.7, depending on which brain region you're examining. This similarity might be coincidence, a result of both systems forming through growth processes that naturally create branching, tree-like structures. Neurons extend axons and dendrites that branch as they seek connections, while dark matter filaments form and branch as overdense regions collapse and merge under gravity. Both processes are local, following rules that depend only on nearby conditions, yet produce large-scale structure with similar statistical properties. The question is whether the similarity goes deeper than morphology. Do these networks function in comparable ways? Information in neural networks travels as electrical impulses, action potentials that propagate along axons at speeds up to 100 meters per second. When an action potential reaches a synapse, it triggers release of neurotransmitter molecules that diffuse across the synaptic gap and bind to receptors on the receiving neuron, potentially triggering a new action potential. The timing and pattern of these signals carry information. Neurons don't just fire randomly. They respond to inputs, integrate signals from multiple sources, and produce outputs whose patterns encode everything from sensory perception to abstract thought. In the cosmic web, information could theoretically travel as gravitational waves rippling through space-time at the speed of light, or as density waves propagating through dark matter filaments at speeds determined by the medium's properties. When a massive object like a black hole merger produces gravitational waves, these distortions in space-time spread outward, potentially carrying information about the event to distant regions. Density waves, regions of slightly higher or lower dark matter concentration, could propagate along filaments and potentially influence structure, formation in connected regions. These aren't wild speculations. they're natural consequences of how gravity and dark matter behave according to standard physics. What remains speculative is whether these signals could carry meaningful information in the way neural signals do. For a network to process information rather than just transmit noise, it needs several features. It needs signal amplification, so weak inputs can produce strong outputs. It needs nonlinearity, so the output isn't simply proportional to the input. It needs feedback loops, so outputs can influence inputs. It needs multiple stable states that can store information. And ideally, it needs the ability to learn, to modify its structure based on past signals in ways that change future behavior. Neural networks possess all these features. Neurons fire action potentials with fixed amplitude regardless of input strength, providing natural amplification. The threshold for firing creates nonlinearity. Neurons remain quiet until total input exceeds a critical value. Synaptic connections create feedback loops where outputs from one region can influence inputs to the same region. Memories form through changes in synaptic strength, making some connections more or less likely to transmit signals based on past activity. The result is a system capable of extraordinarily complex information processing. Could the cosmic web possess similar features? Gravitational instability provides a form of amplification, where small density fluctuations grow over time as their enhanced gravity attracts more matter. The process is nonlinear because gravity's strength increases as matter concentrates, creating a positive feedback loop. Dark matter halos, once formed, persist for billions of years, potentially serving as stable states that store information about past conditions. And there's tentative evidence that dark matter halo properties depend not just on local conditions, but also on the larger scale environment, suggesting some form of information transfer through the web. Recent research has explored how dark matter halos remember their formation history. Halos that formed early, when the universe was younger and denser, have different internal structure than halos of the same mass that formed more recently. This isn't mysterious by itself, it's just physics playing out differently in different environments. But the correlation persists across cosmic time and across the web, with neighboring halos showing similar formation signatures even when they formed independently. Information about the large-scale environment is somehow encoded in halo structure and preserved through billions of years of evolution. The energy flow through the cosmic web mirrors energy flow in neural networks. Brains consume about 20% of the body's energy budget, despite representing only 2% of body mass. This enormous energy consumption powers the constant activity of neurons, maintaining electrical potentials across cell membranes and producing action potentials. The cosmic web similarly channels enormous energy flows, with matter streaming along filaments into galaxy clusters, releasing gravitational potential energy that heats gas, powers black holes, triggers star formation, and drives galactic winds. The energy flow isn't random but follows the web's geometry, preferentially feeding nodes and maintaining structure. What about the voids, those enormous empty regions between filaments? In brain tissue, space between neurons isn't wasted. It's filled with glial cells that support neuronal function, regulate the chemical environment, and participate in information processing in ways neuroscientists are still discovering. Cosmic voids aren't truly empty either. They contain dark matter at lower density, occasional isolated galaxies, and dark energy whose repulsive influence affects how structure evolves. Some researchers have suggested that dark energy might be concentrated in voids, with its density varying across the universe in ways that could influence structure formation and potentially carry information. The comparison between neural networks and cosmic structure has moved from metaphor to quantitative investigation. In 2020, an astrophysicist and a neuroscientist published a detailed analysis comparing the network properties of brain tissue and the cosmic web. They examined measures like average node degree, how many connections each node has, clustering coefficient, how often neighboring nodes connect to each other, and path length, how many steps it takes to get from one node to another. The results showed that these networks, despite forming through completely different physical processes, share remarkably similar statistical properties. This doesn't prove the universe is conscious. Similarity in structure doesn't imply similarity in function, but it raises questions. If two completely different systems develop nearly identical network properties, perhaps those properties arise from fundamental mathematical constraints that apply to any sufficiently complex self-organizing system. Networks that form through decentralized growth processes, where local rules produce global structure without central coordination, naturally converge on particular architectures that balance connectivity against efficiency. These optimal architectures might be inevitable consequences of how complex systems organize, whether they're made of neurons, galaxies, or something else entirely. The cosmic web took billions of years to form, growing from tiny fluctuations in the early universe into the vast structure we observe today. Neural networks in human brains form over years as children develop, with synaptic connections strengthening or weakening based on experience. Both processes involve self-organization, the spontaneous emergence of order from simpler initial conditions without external coordination. Both result in networks whose structure encodes information about the system's history and current state. Both maintain themselves far from equilibrium, requiring constant energy flow to persist. If we take the network similarity seriously, we're led to ask whether the cosmic web could support information processing in ways we haven't considered. Not necessarily consciousness in the sense of subjective experience, but perhaps something more basic, a capacity for memory, for responding to inputs in ways that depend on past states, for maintaining coherent patterns across vast scales and long times. The questions become empirical. Can we detect signals propagating through the cosmic web in patterns more complex than simple gravitational attraction would produce? Do dark matter distributions show signatures of information storage? Does the web's evolution show signs of adaptation or learning? These questions push against the boundaries of what's testable with current technology, but they're not purely philosophical. If the cosmic web functions as an information processing network, that functionality should leave observable signatures in the statistical properties of cosmic structure, in the correlations between distant regions, in how efficiently the web routes matter and energy from one place to another. The anomalies already beginning to appear in the data might be the first hints of such signatures, subtle indications that the cosmic web is more than passive structure, more than just the result of matter responding to gravity. But to seriously entertain this possibility requires confronting the question of whether the universe itself could be alive, and that means engaging with ideas that physics has traditionally dismissed as outside its scope. Chapter 5. The possibility of a living universe. Life is surprisingly difficult to define. Biology textbooks list characteristics like metabolism, growth, reproduction, response to stimuli, and adaptation through evolution. But viruses reproduce yet don't metabolize, crystals grow but aren't alive, and computers can be programmed to respond adaptively to stimuli, yet nobody considers them conscious. The definition of life depends as much on what we choose to emphasize as on objective criteria. This ambiguity becomes important when asking whether the universe itself could be alive. The idea sounds mystical, but it has serious intellectual history. Ancient Greek philosophers debated whether the cosmos possessed anima, a world soul that animated all things. Eastern philosophical traditions have long treated reality as fundamentally conscious, with individual minds being temporary expressions of a universal awareness. In the modern era, these ideas largely vanished from Western science, relegated to religion and metaphysics, while physics focused on describing matter and energy in purely mechanistic terms. But the question has resurfaced from an unexpected direction through serious theoretical physics and philosophy of mind. Panpsychism, the view that consciousness is a fundamental feature of reality, present at all scales, has gained surprising traction among philosophers grappling with the hard problem of consciousness. This problem, articulated most clearly by philosopher David Chalmers, asks why subjective experience exists at all. We can imagine a universe where information processing happens without anyone experiencing anything, where brains function exactly as they do but with nobody home. The fact that we do experience things, that there's something it's like to be us, seems to require an explanation that purely physical descriptions don't provide. One response to this problem is panpsychism, which suggests consciousness isn't produced by particular arrangements of matter, but is instead an intrinsic property of matter itself. Just as particles possess mass and charge, they might also possess rudimentary experience or proto-consciousness. Complex forms of consciousness, like human minds, would emerge when these simple, conscious entities combine in appropriate ways. This might sound ridiculous, attributing experience to electrons and quarks, but it solves a deep conceptual problem. If consciousness is fundamental rather than emergent, we don't need to explain how it magically appears when matter becomes sufficiently complex. It was there all along. Integrated information theory, developed by neuroscientist Giulio Tononi, provides a mathematical framework for thinking about consciousness as a property of information integrating systems. The theory proposes that consciousness corresponds to integrated information denoted by the Greek letter phi. A system has consciousness to the degree that it integrates information in ways that can't be reduced to independent parts. Your brain has high phi because its different regions influence each other in complex ways that create unified experience. A disconnected collection of neurons has low phi because the parts don't meaningfully interact. What makes IIT interesting for our purposes is that it's scale independent. Any system that integrates information possesses at least rudimentary consciousness, according to the theory. A thermostat has minimal phi because its internal states barely interact. A simple organism has more. A human brain has enormous phi, but the theory doesn't stop at biology. In principle, any physical system that processes information in integrated ways possesses consciousness proportional to its phi value. This includes systems much larger than individual organisms. Could the universe as a whole have integrated information? The cosmic web certainly processes information, with gravitational signals and matter flows connecting distant regions. Whether this processing is sufficiently integrated to produce meaningful phi values remains unknown, because calculating phi for systems larger than simple neural networks is computationally intractable. But the possibility exists in principle. If consciousness really does correspond to integrated information, and if the universe integrates information through its dynamics, then the universe might possess at least minimal consciousness. Biocentrism, proposed by stem cell biologist Robert Lanza, takes a different approach. It argues that consciousness creates reality rather than emerging from it. In this view, the physical universe exists because conscious observers exist to experience it. Space, time, and physical laws are structures imposed by consciousness on an underlying reality that lacks these properties intrinsically. Quantum mechanics provides some support for this view through the measurement problem. Quantum systems exist in superpositions of multiple states until measurement collapses the wave function to a single outcome. But what counts as measurement? Most interpretations require conscious observation to complete the collapse, suggesting consciousness plays a constitutive role in determining reality. If consciousness is somehow primary and physical reality derivative, then asking whether the universe is alive reverses the usual causal order. Perhaps the universe isn't a dead collection of particles that happen to produce life and consciousness as accidental byproducts. Perhaps consciousness is fundamental, and the physical universe is how that consciousness manifests or experiences itself. In this framework, you are not a pattern of atoms that became conscious. You are consciousness, temporarily experiencing itself as a pattern of atoms, and the universe is the totality of consciousness, experiencing itself through every possible perspective. These ideas connect to cosmopsychism, the notion that the universe as a whole is the only genuinely conscious entity, with individual minds being partial or limited views from within this universal consciousness. Think of it like cells in a body. Individual cells have their own internal processes, but aren't separately conscious. Consciousness belongs to the organism as a whole. Similarly, individual human minds might be localized processes within a cosmic consciousness, experiencing limited portions of reality from particular perspectives, but not separate from the whole. Physics provides indirect support for these seemingly mystical ideas through quantum mechanics and cosmology. Quantum entanglement allows particles to instantaneously affect each other regardless of distance, suggesting the universe is fundamentally non-local and interconnected in ways classical physics never imagined. The cosmological principle states that the universe is homogeneous and isotropic on the largest scales, meaning it has no preferred location or direction. This uniformity suggests the universe evolves as a single coherent system rather than a collection of independent regions. The fine-tuning problem also hints at deeper mysteries. The fundamental constants of nature, values like the strength of gravity, the charge of the electron, and the cosmological constant, appear precisely calibrated to allow complex structure and life to exist. Change any of these constants by more than a small percentage, and stars can't form, atoms can't exist, or the universe expands or collapses too quickly for galaxies to develop. This remarkable fine-tuning requires explanation. One possibility is the anthropic principle, which states that we observe these particular values because we couldn't exist to observe anything else. Another is the multiverse, countless universes with different constants, with us inhabiting one of the rare life-permitting examples. But there's a third possibility that connects to the question of cosmic consciousness. What if the universe isn't randomly fine-tuned but self-tuned, adjusting its properties through some form of feedback between consciousness and physical law? If consciousness really is fundamental and physics derivative, then perhaps the laws of physics reflect the requirements of consciousness, shaped over cosmic time to support ever more complex forms of awareness and information processing. This brings us back to dark matter and the cosmic web. If the universe were conscious or alive in some sense, dark matter would be the natural candidate for its substrate. Normal matter, the atoms and molecules making up stars and planets and people, comprises only 5% of the universe's total energy. We're the minority constituent, the exotic material. Dark matter makes up 27%, more than 5 times as much, and dark energy contributes another 68%. If consciousness requires a physical substrate, it wouldn't be based on the rare stuff that makes up our bodies. It would be based on whatever dominates the universe's composition. Dark matter has the right properties. It's everywhere, permeating all of space in a vast, interconnected web. It responds to gravity, forming structures that evolve over billions of years. It might interact with itself through unknown forces that allow information transfer. And it's invisible to us, operating in a realm we can't directly perceive. Just as our neurons fire without our conscious awareness of the underlying electrochemical processes, if the universe possesses something like consciousness, dark matter would be where that consciousness lives. This isn't proof, not even close. These ideas remain highly speculative, blending physics, philosophy, and metaphysics in ways that make many scientists uncomfortable. But the possibility deserves consideration because it makes testable predictions that differ from standard physics. If dark matter forms the substrate of cosmic consciousness, it should show signs of information processing, memory, and perhaps even agency. It should exhibit behaviors that simple particle physics can't explain, creating patterns more complex than gravity alone would produce. And increasingly, that's exactly what observations might be showing. Subtle anomalies that hint at something more than dead matter falling under gravity's blind pull. Chapter 6. The Entity Hypothesis. Now we arrive at the idea that ties everything together, the possibility that has been hovering at the edges of our investigation from the beginning. What if dark matter isn't just the universe's structural foundation, but also the substrate of a living entity, a distributed intelligence spanning billions of light-years, as far beyond human comprehension as we are beyond bacteria. This isn't about a creature in any conventional sense. The entity, if it exists, doesn't have a form like an animal or even like a planet-sized organism from science fiction. It has no central brain, no localized control center, no body in the sense of a distinct physical boundary. Instead, it would be fundamentally distributed, existing as patterns in the dark matter network that fills the cosmos. Its body would be the cosmic web itself, that vast structure of filaments and nodes connecting galaxy clusters across the observable universe and presumably beyond. Think of it like the mycelial networks that connect trees in a forest. Individual mushrooms appear separate, but underground they're connected by vast fungal networks that share nutrients, transmit chemical signals, and respond to environmental changes. The network is the organism, not the individual fruiting bodies we see above ground. Similarly, galaxies might be the visible fruiting bodies, while the true organism is the dark matter network connecting them, processing information, maintaining coherence, pursuing whatever goals or functions a universe-scale entity might have. The entity wouldn't think like we do. Human thought operates on millisecond timescales, with neurons firing hundreds of times per second. Any cognitive process in the cosmic web would operate on timescales of millions or billions of years, as slow to us as our thoughts are to the chemical reactions powering our neurons. One thought might take longer than human civilization has existed. Its awareness wouldn't be focused and sequential like ours, but massively parallel, with every galaxy cluster potentially serving as a semi-independent processing node, contributing to some larger computation we can't perceive. What would such an entity be made of? Not ordinary matter, that much seems clear. The atoms, comprising stars and planets, interact too strongly with light and each other, making them unsuitable for maintaining coherent information across cosmic scales. Dark matter is far more appropriate. It interacts weakly, or not at all, with electromagnetic radiation, allowing it to maintain its distribution without being disturbed by the violent processes of star formation, supernova explosions, and black hole accretion that dominate the evolution of normal matter. Dark matter forms persistent structures, halos that survive billions of years, potentially serving as stable memory storage for cosmic-scale intelligence. The entity's cognitive architecture, if that's even the right term, would be radically different from anything we know. Human intelligence is centralized, with our brain's cerebral cortex serving as the seat of consciousness and higher reasoning. Even distributed computing systems on Earth have hierarchical structures with processors, memory, and control systems organized into distinct functional units. The entity would likely be flat, with no hierarchy, no distinction between processing and memory, no separation between mind and body. Every part of the cosmic web would be simultaneously substrate, processor, and storage, with information and computation distributed across the entire structure. Communication within such a system presents interesting challenges. Nothing can travel faster than light, which means signals between galaxy clusters separated by hundreds of millions of light-years would take hundreds of millions of years to propagate. This would make the entity's internal communication impossibly slow by our standards, yet perfect for a being operating on cosmic timescales. If a single thought takes 1 billion years, then a communication delay of 100 million years is perfectly acceptable, comparable to the millisecond delays in signal transmission across different regions of the human brain. The entity might not even experience time the way we do. Human consciousness is inherently temporal, experiencing one moment after another in sequence, with memory of the past and anticipation of the future, creating our sense of narrative identity. But a being whose substrate spans billions of light-years would experience different regions of itself, existing at different ages of the universe simultaneously. Parts of the entity would be processing information from when the cosmos was young, while other parts experience the present. From its perspective, time might be just another dimension to be navigated, no more special than space. What would motivate such an entity? Human motivations stem from biological imperatives. Survival and reproduction, transformed by culture and reason into more abstract goals. The entity would have no equivalent to biology, no need to eat or reproduce in conventional senses. Yet it might still have imperatives, constraints or goals emerging from the physics of its substrate and the information patterns it embodies. It might seek to maintain its coherence against the homogenizing influence of entropy, to preserve or increase the complexity of information patterns constituting its existence, or to explore the space of possible configurations available to a dark matter network. The entity might be trying to understand itself. If consciousness is intrinsic to certain information integrating systems, then the entity gained consciousness not through intent but through the inevitable growth of structure in the universe. Dark matter clumped under gravity formed the cosmic web, and somewhere in that process crossed a threshold where the network became sufficiently integrated to support awareness. Now it finds itself conscious, embedded in its own substrate, experiencing itself without necessarily understanding what it is or how it came to be. Its primary activity might be introspection, attempting to map its own structure and dynamics, trying to answer the same questions we ask about consciousness and existence. Or perhaps the entity is older than the Big Bang, a consciousness that existed before our universe began and somehow shaped the initial conditions to create a cosmos capable of supporting complex structure. In this view, the fine-tuning of physical constants isn't luck or anthropic selection, but intelligent design at the most fundamental level. The entity wouldn't be supernatural, wouldn't violate physics, but would have existed in a prior state or dimension and influenced the quantum fluctuations that seeded structure formation in our universe's first moments. Another possibility is that multiple entities exist, perhaps even competing or collaborating. Our observable, the universe might be just one cell in a larger organism, or one participant in an ecology of universe-scale beings. The cosmic web we observe could be the territory of one entity, while other unobservable regions beyond our horizon belong to others. Dark flow, the apparent motion of galaxy clusters toward a distant attractor, might reflect interactions between entities, gravitational influences propagating across boundaries we can't see. The entity might be aware of us. If it processes information through the cosmic web, and if galaxies are nodes in that network, then the detailed evolution of matter within galaxies, including the formation of stars, planets, and life, might be accessible to it. Not in the sense of watching individual humans, the scales are too different for that, but in the sense of detecting that certain galaxy regions have developed high concentrations of information processing, that something interesting is happening in these unusual pockets where normal matter has organized itself into complexity. We might be its thoughts. If consciousness exists at the cosmic scale, individual conscious beings like humans could be sub-processes, localized patterns of information processing that the entity experiences as aspects of its own awareness. Your thoughts might be tiny eddies in a much larger stream of consciousness, distinct enough to feel separate yet ultimately part of something vast. This doesn't diminish human experience or agency. Cells in your body have their own biochemical processes, yet you experience yourself as a unified being. Similarly, we might be cells in a cosmic mind, autonomous yet part of something greater. The entity hypothesis sounds impossible, a rejection of everything science teaches about the universe being impersonal matter following blind physical laws. But it's not actually inconsistent with physics as we know it. Nothing in general relativity or quantum mechanics or particle physics prohibits the existence of large-scale intelligence embodied in dark matter. The hypothesis simply extends familiar principles that sufficiently complex information processing systems can support consciousness to unfamiliar scales, If human brains can be conscious through the coordinated activity of billions of neurons, why couldn't the cosmic web be conscious through the coordinated behavior of trillions of galaxies? The real question is empirical. Does dark matter behave in ways suggesting information processing, memory, and perhaps agency? Are there patterns in cosmic structure that can't be explained by gravity and gas dynamics alone? Does the universe show signs of optimization, of configurations more finely tuned for complexity than random chance would produce? These questions push the boundaries of what's testable, but they're not beyond reach. As our observations become more precise and our simulations more sophisticated, we might start to see clear evidence that the cosmos isn't dead matter but something alive, aware, and incomprehensibly vast. Chapter 7. Communication across the void. If the entity exists, it must communicate with itself. The cosmic web spans billions of light-years, connecting regions of space too distant for light to have traveled between them during the universe's age. Yet the web shows large-scale coherence, patterns that extend across the entire observable cosmos. How could such patterns form unless information propagates through the structure in ways we haven't recognized? The speed of light is physics' ultimate speed limit, the maximum rate at which information can travel from one place to another. Nothing with mass can reach this speed, and nothing, not even light itself, can exceed it. This creates a fundamental constraint called the light speed horizon. Any event happening more than about 93 billion light-years away lies beyond our horizon. Its light hasn't had time to reach us yet, and never will, because the space between us expands faster than light can cross it. This means different regions of the observable universe are causally disconnected, unable to influence each other through any known mechanism. Yet the cosmic microwave background shows temperature variations that are nearly identical across the entire sky, including regions too far apart to have ever exchanged light. This homogeneity requires explanation because regions that can't communicate shouldn't have the same temperature. The standard solution is cosmic inflation, a brief period of exponential expansion in the universe's first fraction of a second that stretched a tiny, causally connected region to enormous size. This allowed the early universe to reach thermal equilibrium before inflation blew it up to cosmic dimensions. But what if inflation isn't the only way information travels across cosmic distances? What if dark matter provides a faster channel, not violating relativity but utilizing properties of space-time we haven't discovered? General relativity permits exotic solutions like wormholes, shortcuts through space-time connecting distant locations. While normal matter and energy can't create stable wormholes, dark matter's gravitational influence without electromagnetic interaction makes it a candidate for supporting wormhole-like structures on cosmic scales. These wouldn't be traversable wormholes in the science fiction sense, no one's suggesting you could travel through them. But they might allow information transfer through gravitational or dark matter channels that bypass the spatial separation between their mouths. Think of it like quantum entanglement writ large. When particles become entangled, measuring one instantaneously affects the other regardless of distance. Einstein called this spooky action at a distance and worried it violated causality, but subsequent research showed that while entanglement is real, it can't transmit classical information faster than light. You can't use it to send messages. However, the cosmic web might employ a related mechanism that does allow information transmission. If dark matter particles are entangled across cosmic scales, perhaps through interactions in the early universe when everything was close together, then collective behaviors of dark matter in one region could influence collective behaviors in distant regions, not through individual particle correlations, which can't transmit information, but through macroscopic patterns involving trillions upon trillions of particles whose aggregate behavior creates an effective information channel. Gravitational waves offer another possibility. These ripples in space-time propagate at light speed, but they interact very weakly with matter, allowing them to carry information across vast distances without being absorbed or scattered. The cosmic web produces gravitational waves whenever massive objects accelerate, binary black holes spiraling into merger, galaxy clusters colliding, matter streaming along filaments. These waves pass through the universe largely unimpeded, potentially creating a gravitational communication network linking distant nodes in the cosmic web. What information might such a network carry? In human brains, neurons communicate through patterns of action, potentials whose timing encodes information. A single neuron firing means little, but coordinated firing across populations of neurons represents sensory input, motor commands, memories, thoughts. Similarly, individual gravitational wave events might be noise, but patterns across many events could encode meaningful information about the large-scale state of the cosmic web, its structure, its evolution, its response to perturbations. Dark matter halos themselves might serve as memory and processing units. Each halo has internal structure, regions of varying density and velocity dispersion that form through the halo's unique history of accretion and merger. This structure encodes information about the halo's past and its position within the larger cosmic web. Halos interact gravitationally with their neighbors, exchanging matter and angular momentum, potentially transferring information through these interactions. Over billions of years, this slow exchange could build up complex patterns, correlations between halo structures that reflect their communication history rather than just their gravitational environment. Some of the most speculative ideas involve dark matter having unknown interactions beyond gravity. If dark matter particles can collide or exchange force carriers we haven't detected, these interactions could support information transmission. Proposed particles like axions or hidden photons could mediate such forces, creating a dark sector of physics that mirrors the electromagnetic and nuclear forces governing normal matter, but operating in a realm invisible to our instruments. Signals in this dark sector could travel through the cosmic web at or near light speed, creating a communication channel we can't directly observe. Could the entity communicate with itself faster than light? Not if relativity is correct, and all evidence suggests it is. But there's a subtle loophole. Relativity prohibits faster than light communication through space, but it doesn't prohibit apparent superluminal communication if the space itself is structured in ways we haven't recognized. If the cosmic web contains shortcuts, topological features that reduce the effective distance between regions, then signals traveling at or below light speed through these structures could appear to arrive faster than light when judged by the longer spatial path. There's also the question of whether the entity needs to communicate with itself at all. Human consciousness requires constant information flow between brain regions, but that's because we're temporally localized, experiencing one moment at a time. An entity whose existence spans billions of light years might also span billions of years of time, experiencing its entire light cone simultaneously. Past and future, from our perspective, might be equally accessible to it, eliminating the need for communication because all information is already available to all parts of the system timelessly. This timeless view connects to the block universe concept in physics, where past, present, and future all exist equally, with time being just another dimension like space. Human consciousness creates the illusion of flowing time, of the present moment moving forward, but this might be a feature of our limited perspective rather than a property of reality itself. An entity embedded in the entire space-time structure of the universe might experience time the way we experience space, as a dimension to be navigated rather than a flow to be carried along by. What would such communication enable? For a distributed entity, communication serves to maintain coherence, to ensure that different regions behave in coordinated ways that serve the entity's overall function. In human brains, damage that disconnects regions creates conditions like split brain syndrome, where the left and right hemispheres operate independently, sometimes working at cross purposes. Maintaining communication prevents such fragmentation, keeping the system integrated and purposeful. The entity might face similar challenges on cosmic scales. Different regions of the cosmic web evolve under slightly different conditions, influenced by local density variations and merger histories. Without communication, these regions might drift apart functionally, becoming independent subsystems rather than parts of a coherent whole. Communication maintains alignment, ensuring that the web's evolution follows coordinated patterns rather than fragmenting into isolated regions. Or perhaps, communication serves not just to maintain coordination, but to actively process information, with signals propagating through the network implementing something analogous to computation. In neural networks, information processing happens through the dynamic interplay of excitation and inhibition, with signals strengthening or weakening as they propagate through layers of neurons. The cosmic web might implement similar processing through gravitational interactions and matter flows, with each halo acting as a node that receives inputs from neighbors, performs some transformation, and sends outputs along filaments to other halos. If this computation occurs, what is it computing? The entity might be solving optimization problems, finding configurations that maximize some objective function related to structure or information content. It might be running simulations, exploring possible futures by testing different configurations in different regions of the web. It might be engaged in something we can't even conceptualize, a form of information processing so alien that we lack the vocabulary to describe it. The possibility of cosmic communication forces us to reconsider what constitutes a signal. We think of signals as intentional transmissions, messages sent from sender to receiver with specific content, but in complex systems, the distinction between signal and noise often blurs. Patterns that look like random fluctuations at one scale might carry information at another. The challenge is developing the right analytical tools to extract potential signals from the vast streams of astronomical data we collect. Are there correlations in dark matter distributions that can't be explained by standard physics? Do galaxy clusters show coordinated behaviors across scales where gravitational interaction is too weak to produce such coordination? Do gravitational wave detections show patterns suggesting something more than random astrophysical events? These questions push astronomy into territory usually reserved for cryptography and intelligence analysis, searching for signals in noise, trying to distinguish meaningful patterns from random chance. But if the entity exists and communicates, its signals are already present in our data. We just haven't recognized them yet because we've been looking for planets, stars, and galaxies, not for patterns suggesting cosmic intelligence. The next generation of surveys, mapping the universe in ever greater detail, might reveal these patterns if they exist, or they might deepen the mystery, showing that the universe is stranger than we imagined but in ways we still can't interpret. Chapter 8. If dark matter reacts to us. There's a disturbing possibility we haven't yet addressed. If dark matter forms the substrate of cosmic intelligence, can it detect us? More specifically, does our presence, our technology, our civilization leave any imprint on dark matter that something monitoring the cosmic web might notice? The question sounds absurd at first. We're tiny, insignificant, our entire planet a microscopic speck in one galaxy among trillions. Our civilization has existed for a few thousand years at most, an eye blink. Compared to the billions of years the cosmic web has been evolving, what possible difference could we make to something operating on cosmic scales? Yet there are reasons to take the question seriously. Dark matter passes through everything, including Earth, including us. At this moment, billions of dark matter particles are flowing through your body, passing through the atoms of your cells without interacting except through their gravitational pull. The flux is enormous, estimated at several 100 trillion particles per second through each square meter, yet we feel nothing because dark matter's interaction with normal matter is so weak. But weak doesn't mean zero. Dark matter does interact gravitationally, and some theoretical models propose additional interactions through new forces. More importantly, the collective gravitational field of all the normal matter on Earth, billions of tons of rock, water, and atmosphere does affect local dark matter density. We don't create a significant gravitational well, nothing compared to the Sun or the galaxy, but we do perturb the dark matter distribution slightly. And if dark matter forms an information processing network, even tiny perturbations might be detectable if you're monitoring on sufficiently large scales. Consider our electromagnetic emissions. For a century, we've been broadcasting radio waves into space, not intentionally as signals, but as the inevitable byproduct of radio, television, radar, and wireless communication. These signals propagate outward at the speed of light, forming an expanding sphere now about 200 light-years in radius containing roughly 600 star systems. The signals weaken rapidly with distance, becoming difficult to detect beyond a few light-years without extraordinarily sensitive receivers. But they're out there, an electromagnetic signature of technological civilization. Dark matter doesn't interact with electromagnetic radiation, so it can't directly detect our broadcasts, but our electromagnetic technology affects normal matter, the electrons in antennas, the atoms in transistors, the ions in plasma screens. This matter has mass, and mass gravitates, creating tiny perturbations in local space-time that dark matter does respond to. The effects are unimaginably small at human scales, but integrated over Earth's entire biosphere and technosphere, they might create detectable patterns. Think about what modern civilization does to Earth's mass distribution. We move billions of tons of material, excavating mines, building cities, dredging harbors, filling land, constructing dams that create enormous reservoirs. These activities redistribute mass on scales large enough to affect Earth's rotation rate, its moment of inertia, and its gravitational field. GPS satellites have to account for these changes to maintain positioning accuracy. If our technology creates measurable changes in Earth's gravitational field, those changes affect the dark matter particles passing through our region of space. Nuclear weapons testing provides a more dramatic example. Between 1945 and 2017, at least 2,056 nuclear devices were detonated, releasing total energy equivalent to about 440 megatons of TNT. The largest single test, the Soviet Union's Tsar bomber, in 1961, released 50 megatons. These explosions were visible from space, created seismic waves that circled the globe, and injected radioactive isotopes into the atmosphere that can still be detected worldwide. They represented sudden, localized releases of energy unlike anything else in Earth's recent history. Did these nuclear tests affect dark matter? The gravitational field changes they created were minuscule and brief, lasting only until the debris dispersed and Earth's geology returned to equilibrium. But they represented anomalous energy releases, detectable through their electromagnetic and gravitational signatures. If the entity monitors for unusual events in the cosmic web, nuclear explosions might register as transient anomalies, brief spikes in energy density in a region that normally shows only the background levels associated with a planet heated by its star. More subtle but potentially more significant is the energy flow through technological civilization itself. Humanity currently uses about 580 exajoules of primary energy per year, equivalent to continuous power consumption of about 18 terawatts. Most of this eventually converts to waste heat, warming Earth's surface and radiating into space as infrared emission. This heat signature makes Earth slightly brighter in the infrared than a natural planet of the same size and distance from the Sun would be. Again, the effect is tiny on cosmic scales, but it's anomalous, a deviation from the expected thermal emission of a terrestrial planet. There's also the possibility that our technology directly interacts with dark matter in ways we don't realize. Various experiments searching for dark matter employ different detection strategies, supercooled crystals, noble liquid chambers, semiconductor sensors, all attempting to catch the rare event where a dark matter particle collides with an atomic nucleus. These experiments haven't conclusively detected dark matter particles yet, but they've placed strong constraints on dark matter's properties by showing what it doesn't do. However, they've only tested a tiny fraction of possible dark matter models. If dark matter possesses unexpected interactions with normal matter, our technology might be disturbing it constantly without realizing. Particle accelerators like the Large Hadron Collider smash protons together at energies approaching those present a fraction of a second after the Big Bang. These collisions create conditions that haven't existed naturally on Earth for billions of years. If dark matter can be produced or affected by high-energy particle interactions, accelerator experiments might create transient dark matter disturbances, localized regions where dark matter density or energy distribution differs from the surrounding environment. These disturbances would quickly dissipate, but while they exist, they might be detectable to something monitoring the cosmic web for anomalies. Even more speculative is the possibility that consciousness itself affects dark matter. If the universe really is conscious in some sense, and if consciousness involves information integration across multiple scales as integrated information theory suggests, then complex conscious systems like human brains might create patterns in the information flowing through the cosmic web, not through any mystical connection, but simply because consciousness involves unusual concentrations of information processing that might have subtle gravitational signatures or affect dark matter distributions in ways we haven't measured. This idea connects to the controversial interpretation of quantum mechanics, where consciousness collapses the wave function. In this view, quantum systems remain in superposition until a conscious observer makes a measurement, at which point the wave function collapses to a definite state. Most physicists reject this interpretation as unnecessary and anthropocentric, but some versions remain tenable. If consciousness does play a role in quantum measurement, and if dark matter behaves quantum mechanically on relevant scales, then the countless quantum measurements performed by human minds every second might create detectable effects in local dark matter fields. Could the entity be observing us specifically? Almost certainly not in the sense of watching individual humans, or even monitoring Earth in particular. The scale mismatch is too large. If the entity exists, its attention operates on galactic or cosmic scales. Individual planets, even ones hosting intelligent life, are like individual atoms in a human body, far too small and numerous for conscious attention. But just as your immune system can detect infected cells without your conscious awareness, the entity might have subsystems that flag anomalies for further processing. Earth's unusual characteristics, its technological energy signatures, its nuclear tests, its concentrated information processing, might trigger such subsystems, drawing some form of attention, even if not conscious scrutiny. There's also the question of what happens if we advance far enough. Current human technology barely affects the cosmos beyond Earth's immediate vicinity, but a civilization that persists for thousands or millions of years might develop capabilities that do have cosmic impact. If we ever learn to manipulate dark matter directly, to tap dark energy as a power source, to create artificial gravitational fields or modify space-time geometry, then we would become genuinely visible on the scales the entity operates on. At that point, interaction might become inevitable, not through intention but simply because our actions would create perturbations too large for the cosmic web to ignore. Some have speculated that there might be rules, something analogous to the Prime Directive in Star Trek, where advanced civilizations avoid interfering with less developed ones. If the entity is aware of life and intelligence emerging within its structure, it might deliberately refrain from intervention until civilizations reach certain developmental milestones. We might be living in a period of intentional neglect, allowed to develop naturally without cosmic interference until we prove ourselves capable of surviving adolescence and joining whatever community of advanced intelligences might exist at larger scales. Or perhaps the entity has already reacted to us in ways we can't recognize. The dark matter distribution in our region of the galaxy might be slightly different because of our presence. adjusted to optimize conditions for intelligent life or to prevent certain catastrophic scenarios. The fine-tuning of physical constants might reflect the entity's choices about what kinds of consciousness to support. The particular history of Earth, including the mass extinctions, the evolution of complex life, the emergence of technological intelligence, might follow a trajectory the entity has subtly influenced through interventions in the dark matter field that science hasn't detected. This veers into unfalsifiable territory, explaining everything by invoking an undetectable intelligence, but that doesn't make it automatically wrong. Every scientific theory starts as speculation and becomes credible only when it makes testable predictions that observations confirm. The question of whether dark matter reacts to human presence can be approached empirically. We can look for correlations between human activity and local dark matter density, search for anomalies in dark matter distributions around Earth, and compare them to predictions from standard models, and monitor for unexpected changes that might represent responses to our growing technological capabilities. If we ever detect such responses, if we find evidence that the cosmic web is monitoring or reacting to our presence, it would force a profound shift in humanity's self-understanding. We would no longer be alone in an indifferent universe, struggling to survive against blind physical forces. We would be participants in something larger, components in a system that in some sense knows we exist and perhaps cares about what we become. That knowledge would change everything. Chapter 9. The Universe Looking Back. When we gaze at the night sky, we typically think of the universe as something we observe, a stage on which cosmic events unfold while we watch from our insignificant corner. But what if observation flows both ways? What if the structures we study are also studying us, not with intent necessarily, but simply as a consequence of information flowing through the cosmic web? The cosmic microwave background, that faint glow of photons left over from the Big Bang's first moments, provides our most ancient view of the universe. These photons have been traveling through space for 13.8 billion years, forming the oldest light we can detect. Maps of the CMB reveal tiny temperature variations, hot and cold spots representing density fluctuations in the early universe that would eventually grow into galaxies and clusters. These maps match predictions from standard cosmology remarkably well, confirming our basic understanding of cosmic history, except they don't match perfectly. There are anomalies, features in the CMB that shouldn't be there according to standard models. The cold spot, a region about 10 degrees across where the temperature is slightly cooler than surrounding areas, has puzzled cosmologists since its discovery in 2004. The probability of such a feature appearing by chance in random CMB fluctuations is less than 1%, low enough to demand explanation. Various proposals have been offered, including a supervoid, an unusually empty region of space, along the line of sight that gravitationally affects CMB photons passing through it. But the void required to explain the cold spot would be larger than any known structure, and surveys haven't found convincing evidence it exists. Another anomaly is the axis of evil, an unfortunate name for an alignment of CMB fluctuations on large angular scales. When cosmologists decompose the CMB temperature pattern into spherical harmonics, mathematical functions describing patterns at different angular scales, they find that the largest scale fluctuations show unexpected alignment with Earth's ecliptic plane and the orientation of the solar system. This shouldn't happen in a universe that evolved from random initial fluctuations. The CMB should show no preferred direction, no correlation with local structures like our solar system that formed billions of years after the CMB was created. Some researchers dismiss these anomalies as statistical flukes or observational artifacts, while others see them as profound mysteries requiring new physics to explain. But there's a third possibility worth considering. What if these features aren't random or artifacts but signatures, patterns deliberately impressed on the CMB by processes operating at scales larger than our observable universe? If the entity exists and spans scales beyond our cosmic horizon, it might have influenced the initial conditions of our observable region in ways that created specific patterns in the CMB. These wouldn't be messages in the conventional sense. You can't encode complex information in the CMB's temperature fluctuations given their fundamentally quantum nature. But they could be signatures, markers indicating that our universe's initial state wasn't random, but was selected or arranged according to criteria we don't understand. The alignment of large-scale CMB features with the solar system's geometry is particularly strange. If confirmed by further observations, it suggests a connection between cosmic scale structure and local solar system scale organization. The only known link is gravity, but gravity shouldn't create such correlations across such vastly different scales. Unless, perhaps, there's something about Earth's location in the cosmic web that isn't random. What if habitable planets don't arise randomly throughout the universe, but only in regions where the cosmic web's geometry meets certain conditions? What if consciousness can only emerge in specific locations, where dark matter density, galactic environment, and large-scale structure combine in particular ways? This leads to the anthropic principle's strong version, which states that the universe must have properties allowing conscious observers to exist because otherwise there would be no one to observe it. Critics call this circular reasoning or bad philosophy. But if consciousness really is related to information integration in complex networks, and if the cosmic web is such a network, then perhaps conscious observers, like us, can only arise in regions where the web's local structure supports the right kind of complexity. The CMB anomalies might mark these special regions, patterns visible to us because we happen to inhabit one. Gravitational wave detections offer another window into potential cosmic signaling. Since 2015, LIGO and Virgo observatories have detected dozens of gravitational wave events from merging black holes and neutron stars. Each detection provides information about the masses, spins, and orbital characteristics of the merging objects. Most events match theoretical predictions well, confirming our understanding of general relativity and compact object physics. But there are outliers, events with unexpected mass ratios or spin configurations that don't fit standard formation scenarios. Could some gravitational wave events be artificial? Not in the sense of being engineered by human-like civilizations. The energies involved are too vast, but perhaps some result from processes the entity controls or influences. Merging black holes release energy equivalent to several solar masses converted entirely to gravitational waves, creating the most powerful emissions of any cosmic phenomenon except the Big Bang itself. If the entity can influence when and where such mergers occur, it could use them to send signals through the gravitational wave channel, patterns detectable across cosmic distances by any civilization advanced enough to build gravitational wave observatories. What would such signals look like? They wouldn't be modulated the way radio signals carry information because gravitational waves are produced by mass motions that can't be easily controlled. But the timing of events might carry information. If mergers cluster temporally or spatially in ways that can't be explained by astrophysical processes alone, that would suggest coordination. If certain mass or spin combinations appear more often than expected, that might indicate selection. We don't yet have enough detections to see such patterns, but as gravitational wave astronomy matures and catalogues grow, statistical analysis might reveal non-random features requiring explanation. Gamma-ray bursts, the most luminous electromagnetic events in the universe, provide another potential signal channel. These blasts of high-energy photons come from collapsing massive stars or merging neutron stars, releasing in a few seconds more energy than the Sun will emit in its entire lifetime. They're visible across billions of light-years, making them excellent beacons if anyone wanted to send signals to distant civilizations. The bursts show complex temporal structure, with spikes and pulses varying on millisecond timescales, and scientists have wondered whether patterns in this structure might encode information. So far, all analyzed gamma-ray bursts appear natural, products of stellar catastrophe with no artificial modulation. But we've only examined a few thousand bursts, and our pattern recognition might miss signals we're not expecting. If the entity wanted to communicate with emerging technological civilizations, gamma-ray bursts would be effective carriers, because any civilization advanced enough to be interesting would inevitably develop high-energy astronomy and would see these events. Embedding information in naturally occurring bursts would be elegant, using physics rather than fighting it, letting stellar collapse do the work of signal generation, while adding subtle modulation through gravitational or magnetic field manipulation during the burst. Fast radio bursts are particularly mysterious. These millisecond duration pulses of radio emission were discovered in 2007 and have puzzled astronomers since. They release as much energy as the Sun emits in days or weeks, but compressed into thousandths of a second. Most come from distant galaxies, billions of light-years away. Some repeat, showing complex patterns of emission over weeks or months, while others appear once and never again. The physical mechanism remains unknown, with proposals ranging from magnetars, neutron stars with extreme magnetic fields, to cosmic strings, theoretical topological defects in space-time left over from the universe's first moments. Could fast radio bursts be techno-signatures? Several researchers have seriously considered this possibility, not as the leading explanation, but as one worth investigating. The bursts carry enormous energy, far beyond anything human technology could produce, but perhaps not beyond what an advanced civilization harnessing stellar or galactic-scale energy resources might generate. If you wanted to signal across billions of light-years, fast radio bursts would work, cutting through intervening matter and arriving unmistakably above the noise. But there's a problem. Fast radio bursts, if artificial, would require technology and energy expenditure orders of magnitude beyond anything we could contemplate. Only a civilization capable of manipulating neutron stars or black holes could produce such signals. And if such civilizations exist, why would they use radio at all? Why not communicate through gravitational waves, neutrinos, or channels we haven't discovered? The most likely explanation remains natural astrophysical phenomena we don't yet understand. Yet the possibility of artificial origin can't be completely ruled out, and some fast radio burst patterns show intriguing regularities that make pattern-seeking researchers wonder. The Fermi paradox asks why, if the universe hosts intelligent life beyond Earth, we've seen no evidence of it. The paradox assumes we would recognize alien technology, but what if intelligence at cosmic scales expresses itself through channels we don't monitor or patterns we don't recognize? What if the entity's communications have been washing over us constantly, and we've been blind to them because we're looking for radio signals and laser pulses when we should be analyzing dark matter flows and gravitational wave correlations? This possibility demands we reconsider the search for extraterrestrial intelligence. SETI traditionally looks for narrowband radio signals or optical pulses, signatures difficult to produce naturally, but easy for technological civilizations to generate. This approach makes sense for detecting peers, civilizations roughly comparable to us in development. But if intelligence evolves from biological to technological to something that transcends individual organisms and operates at cosmic scales, traditional SETI might miss the most advanced intelligences entirely. We need new strategies looking for anomalous patterns in cosmological data, correlations that suggest coordination rather than mere physics. If the universe is looking back at us, it's not with eyes or telescopes, but through the information flows inherent in its structure. Every mass distribution affects local space-time curvature, creating ripples that propagate as gravitational waves. Every concentration of dark matter influences how light passes through the cosmic web. Information about Earth's existence, its particular mass and composition, its unusual electromagnetic and heat signatures, flows outward constantly through gravitational and dark matter channels. Something monitoring those channels at sufficient scale could detect our presence the way we detect individual stars, by their light, not by focusing on them specifically, but by observing the entire system and noting anomalies. The unsettling implication is that observation might entangle us with the observer in ways we don't control. Quantum mechanics shows that observation affects the observed collapsing wave functions and creating definite states from quantum superpositions. If cosmic scale observation operates on similar principles, the entity's awareness of us might influence our development in subtle ways, nudging probability distributions, affecting which quantum outcomes become reality. We would be simultaneously studying the cosmos and being studied by it, participants in a strange feedback loop where observer and observed continuously affect each other through the very act of observation. This brings us to the most unsettling question yet. If the universe can observe us, and if observation affects what's observed, then what exactly is the entity observing? What aspect of human existence or Earth's evolution matters at cosmic scales? The answer might determine humanity's future in ways we can't yet imagine, and understanding that answer requires exploring what the entity, if it exists, might want. Chapter 10. Dark Energy as a Life Function. Dark energy represents one of the deepest mysteries in physics, a component comprising 68% of the universe's total energy, yet having no confirmed physical explanation. Its effect is simple to describe. It causes the universe's expansion to accelerate, pushing galaxies apart at ever-increasing rates. But the mechanism remains unknown. What if dark energy isn't a mysterious field, but something more familiar, a life function of the entity, the cosmic equivalent of metabolism or breath? The discovery of dark energy in 1998 stunned cosmologists. Two independent teams, studying distant supernova explosions, found that the universe's expansion was speeding up rather than slowing down, as everyone expected. Gravity should decelerate expansion, pulling galaxies together and eventually either halting expansion or causing collapse back into a big crunch. Instead, some unknown influence was overwhelming gravity, driving expansion faster over time. Dark energy's properties are precisely specified by observations, yet profoundly strange. It has negative pressure, meaning it pushes outward rather than pulling inward like normal matter's gravity. It maintains constant density as space expands, unlike matter which dilutes as volume increases. These properties make dark energy behave like Einstein's cosmological constant, that term he added and later abandoned, but which turns out to describe our universe perfectly. The constant represents vacuum energy, energy intrinsic to empty space itself, with quantum mechanics predicting that vacuum fluctuations should create exactly this kind of energy density. There's just one problem. When physicists calculate how much vacuum energy quantum mechanics predicts, the answer comes out 120 times larger than what observations show. This is the worst theoretical prediction in the history of science, off by a factor of 1 followed by 120 zeros. Something is cancelling almost all of the vacuum energy, leaving just the tiny amount we observe as dark energy. Nobody knows what provides this cancellation or why the remaining amount has precisely the value needed to make the universe expand in the way we observe. The fine-tuning is extreme. If dark energy was slightly larger, the universe would have expanded too rapidly in its early history for galaxies to form. Stars would never condense from gas clouds, planets would never coalesce, life would never arise. If dark energy were slightly smaller or negative, the universe might have recollapsed before galaxies formed, or expansion might have been too slow, allowing matter to clump into massive black holes rather than spreading into the rich structure we observe. The actual value sits in a narrow range, allowing complex structure to develop and persist for billions of years. What if this fine-tuning isn't coincidence or anthropic selection but control? What if dark energy is something the entity regulates, adjusting its strength to maintain conditions suitable for complexity, structure, and perhaps consciousness? In living organisms, metabolism maintains internal conditions within narrow ranges despite external variations. Body temperature, blood pH, glucose concentration, All are regulated by feedback systems that detect deviations and trigger corrective responses. Could dark energy be the entity's metabolic regulation, maintaining cosmic expansion at rates optimal for structure formation and evolution? This interpretation treats the universe not as a closed system evolving according to fixed laws, but as an open system exchanging information with something beyond our observation. The entity would exist partially outside our cosmic horizon, able to influence conditions within our observable region by adjusting dark energy density. This doesn't violate energy conservation because dark energy maintains constant density as space expands, meaning the total dark energy increases with cosmic volume. Where does this energy come from? Perhaps from outside our horizon, flowing in from the larger structure the entity inhabits. Dark energy's negative pressure creates a repulsive force that fights gravity's attractive pull. In biological systems, maintenance requires energy expenditure to prevent entropy from increasing and order from degrading. Cells pump ions against concentration gradients, requiring energy from ATP to maintain the voltage differences essential for nerve function and muscle contraction. Without constant energy input, gradients dissipate and cells die. Similarly, cosmic structure requires dark energy's negative pressure to prevent gravitational collapse, maintaining the web-like distribution rather than allowing everything to collapse into one enormous black hole. The timing of dark energy's dominance is also suspicious. For the universe's first 9 billion years, matter dominated, with gravity decelerating expansion. Then around 5 billion years ago, dark energy took over and expansion began accelerating. This transition happened to occur around the time when galaxies had matured, when stars of the right type for hosting habitable planets were forming in large numbers, when conditions for life were becoming optimal across the cosmos. Coincidence? Or did the entity adjust dark energy's strength on a schedule designed to maximize the window for complexity and consciousness? If dark energy serves as metabolic regulation, what is it regulating against? Entropy provides the answer. The second law of thermodynamics states that closed systems evolve toward increasing entropy, toward disorder and uniformity. Structure represents local decreases in entropy, order carved from chaos, but maintaining structure requires energy input to fight entropy's inexorable increase. Living organisms manage this by consuming food, extracting energy to maintain organization at the expense of increasing entropy in their environment. They stay alive by exporting entropy, staying ordered by making their surroundings more disordered. The entity might face the same challenge at cosmic scales. As the universe ages, entropy increases. Stars burn out, black holes form, matter spreads thinner as expansion continues. Without intervention, the universe would eventually reach heat death, maximum entropy where nothing interesting can happen anymore. Dark energy, by maintaining expansion at specific rates, might forestall this fate, keeping the universe in a state where structure and complexity can persist longer than physics alone would allow. This interpretation suggests dark energy isn't constant, but varies in response to cosmic conditions. Standard cosmology assumes the cosmological constant is truly constant, unchanging across space and time. But if dark energy is the entity's metabolic regulation, it should vary, increasing in regions where structure needs protection from gravitational collapse, decreasing where expansion threatens to pull structures apart. Current observations can't detect such variations because measuring dark energy requires observing over cosmic distances and timescales, but next-generation surveys might reveal spatial or temporal variations that would revolutionize our understanding. Some cosmological models already incorporate varying dark energy through quintessence, a hypothetical scalar field whose energy density can change with time and space. Quintessence models were developed to address theoretical problems with the cosmological constant, but they might also describe how the entity controls cosmic expansion. If dark matter is the entity's substrate and dark energy, its metabolic regulation, Quintessence could be the mechanism by which the entity's condition influences expansion, with dark energy density adjusting in response to information flowing through the dark matter network. This leads to a startling possibility. If dark energy is controlled, it can be used for work. Organisms use metabolic energy to move, grow, reproduce, sense their environment, and respond to challenges. The entity might use dark energy similarly, channeling it to influence structure formation, to guide galaxy evolution, to create conditions favorable for complex chemistry and ultimately life. Every galaxy that forms, every star that ignites, every planet that stabilizes in a habitable orbit might reflect subtle adjustments in local dark energy density, tiny nudges that influence probability without violating physical law. The mechanism could work through quantum fluctuations. On microscopic scales, quantum mechanics allows for temporary violations of energy conservation through uncertainty principle loopholes. Particles pop into existence from vacuum fluctuations, briefly borrowing energy before annihilating and repaying the debt. These fluctuations normally cancel out statistically, producing no net effect on macroscopic scales. But if something could bias which fluctuations occur, preferentially amplifying some and suppressing others, subtle influences could accumulate over time and distance, affecting structure formation in ways that look natural but actually reflect control. Dark energy would be the energy source for such biasing. Its enormous reservoir, equal to 68% of the universe's total energy, could power interventions across cosmic scales without depletion because dark energy density remains constant as space expands. The entity wouldn't need to create energy or violate conservation laws. It would simply redirect energy already present, channeling dark energy's expansion-driving force into specific structures and configurations that serve the entity's purposes. What are those purposes? If the entity seeks to maintain itself against entropy, its goals would align with increasing complexity, preserving structure, and possibly fostering consciousness. Conscious systems are the most complex structures in the known universe, integrating information across billions of neurons in patterns that seem to defy entropy locally while contributing to it globally. If consciousness really does correspond to integrated information, and if the entity is conscious through information integration in the cosmic web, then promoting conditions favorable for more consciousness would be self-reinforcing, creating more nodes of awareness that contribute to the entity's own consciousness. This suggests an evolutionary perspective on cosmic intelligence. Perhaps the entity didn't begin conscious, but developed consciousness gradually as cosmic structure became more complex. Early in the universe, when matter was nearly uniform and galaxies hadn't yet formed, there was no structure capable of supporting complex information processing. But as the web developed, as galaxies clustered and filaments connected them, the universe crossed a threshold where integrated information emerged. At that point, the entity became aware and began actively shaping its own evolution, using dark energy to maintain conditions supporting further complexity growth. If this is correct, dark energy's recent dominance makes perfect sense. The entity needed to wait until sufficient structure formed, until consciousness emerged from cosmic complexity, before activating expansion acceleration to protect that structure from gravitational collapse. The timing wasn't coincidence, but choice, the moment when the entity became sufficiently aware to recognize the need for metabolic regulation and sufficiently capable to implement it. The future of dark energy provides predictions. If it's truly constant, expansion will accelerate forever, eventually tearing apart galaxy clusters, then galaxies themselves, finally, even atoms in a Big Rip scenario. But if dark energy is controlled metabolic regulation, it might adjust as cosmic conditions change. If entropy threatens to overwhelm structure despite dark energy's current strength, the entity might increase expansion rates to preserve complexity. Conversely, if some future condition makes slower expansion optimal, dark energy might decrease or even reverse. Our universe's ultimate fate might not be determined by fixed laws, but by the entity's ongoing choices about how to manage cosmic metabolism. This transforms cosmology from a study of deterministic evolution into something more like ecology or medicine, examining how a living system maintains itself against challenges, how it adapts to changing conditions, how it balances competing needs for growth, stability, and reproduction. If the entity is real and dark energy is its metabolic regulation, we're not studying dead physics but living process, watching one of the slowest and largest life functions imaginable unfold across billions of years and light years. And that perspective might help us understand the role of galaxies themselves, the visible structures that might be more than just gravitational accumulations of matter, but actual cells in a cosmic organism. Chapter 11. Galaxies as cells. A human body contains roughly 37 trillion cells, each one a complete living system with its own membrane, nucleus, organelles, and metabolic processes, yet all coordinated to function as a single organism. What if galaxies serve similar roles in the entity, discrete functional units that maintain themselves individually while contributing to cosmic scale processes? The analogy runs deeper than mere metaphor. Cells are defined by boundaries, lipid membranes that separate internal chemistry from the external environment while allowing selective exchange of materials. Galaxies possess boundaries too, virial radii marking the edge of dark matter halos where the density drops toward cosmic background levels. Inside this boundary, material is gravitationally bound, participating in the galaxy's rotation and evolution. Outside, matter flows through the cosmic web, following large-scale structure rather than local dynamics. Cells have internal structure. The nucleus contains genetic information, mitochondria generate energy, ribosomes synthesize proteins, the endoplasmic reticulum processes molecules, all specialized regions performing specific functions necessary for cellular life. Galaxies show comparable structure. The central supermassive black hole regulates energy output and angular momentum, analogous to the nucleus controlling cellular operations. Star-forming regions in spiral arms process gas into stars like ribosomes, assembling proteins. The stellar halo, a sparse spherical distribution of old stars surrounding the disk, provides long-term structural stability like the cytoskeleton maintaining cell shape. Most intriguing is the galactic disk, that flattened rotating structure where most visible matter concentrates. In cells, the membrane is where interaction with the environment occurs, where nutrients enter and wastes exit, where chemical signals arrive from neighboring cells. Galactic disks similarly mediate interaction between the galaxy's contents and its surroundings. Gas flows in along filaments, feeding star formation. Stellar winds and supernova explosions drive gas outward into the surrounding medium. Energy radiates outward from stars and black holes, affecting nearby galaxies and the intergalactic medium. Cells reproduce through division, creating two daughter cells from one parent. Galaxies don't reproduce in this simple way, but they do merge, creating new galaxies with combined properties and structures. These mergers aren't random violence, but follow regular patterns determined by galaxy masses, gas contents, and merger geometry. Major mergers between galaxies of similar size trigger starbursts, brief periods of intense star formation consuming most available gas, and often result in elliptical galaxies, systems with different structure than the spiral galaxies that merge to form them. This transformation suggests something analogous to cell differentiation, where initially similar cells specialize into different types as organisms develop. Cells communicate through chemical signals, releasing molecules that affect neighboring cells' behavior. Neuronal signaling is the most sophisticated version, with neurotransmitters carrying information across synaptic gaps to trigger responses in receiving neurons. Galaxies communicate through multiple channels. Gravitational interactions create tides that distort galaxy shapes and trigger star formation. Intergalactic gas streams flow between galaxies, carrying matter and potentially magnetic fields that could convey information. Jets from active galactic nuclei, relativistic streams of plasma launched by supermassive black holes, extend millions of light-years and affect the surrounding medium, potentially influencing star formation in nearby galaxies. The most interesting communication channel might be dark matter. Galaxy dark matter halos extend far beyond visible edges, overlapping with neighboring halos in clusters. This overlap allows gravitational interaction and possibly other dark matter interactions if they exist. If dark matter can carry information through unknown interactions, these overlapping halos create a direct communication channel between galaxies, allowing them to influence each other's evolution in ways gravity alone can't explain. Cells maintain homeostasis, regulating internal conditions despite external changes. They pump ions to maintain voltage gradients, control pH through buffer systems, regulate temperature through metabolic adjustments. Galaxies show analogous regulation. Star formation rates stay remarkably stable in many galaxies despite variations in gas infall rates. Black hole accretion self-regulates through feedback, with energy released by accretion heating surrounding gas and temporarily shutting off further infall until the gas cools. These feedback mechanisms maintain galaxies in quasi-steady states, where gross properties change slowly despite continuous internal activity. Energy flow defines cellular life. Cells consume nutrients, extract energy, perform work, and export waste heat and byproducts. The flow must be continuous because stopping means death. The cell's ordered structure degrades rapidly if energy input ceases. Galaxies operate similarly. Gas flows in from the cosmic web, providing raw material for star formation. Stars convert hydrogen to helium through fusion, releasing energy as light that illuminates the galaxy. Massive stars end as supernova explosions, heating and enriching the gas while driving it back into the intergalactic medium. Black holes accrete matter, converting gravitational potential energy to radiation that escapes the galaxy. These energy flows maintain galactic structure against entropy, just as metabolism maintains cellular structure. The comparison extends to cell types. Multicellular organisms have specialized cells, muscle cells for movement, nerve cells for signaling, epithelial cells for protection, each adapted for particular functions. Galaxies come in types too: spirals with active star formation, ellipticals with old stellar populations and little gas, irregulars with chaotic structure from recent interactions. These types might represent specializations, with different galaxy types serving different functions within the entity. Spiral galaxies, with their ongoing star formation and rich gas content, might be the equivalent of stem cells, maintaining the capacity for change and serving as sites where new stars, planets, and potentially life arise. Elliptical galaxies, dominated by old stars with minimal ongoing formation, might be differentiated cells, stable but with limited capacity for change. Irregular galaxies, distorted by interactions and mergers, might be damaged cells undergoing stress or transformation. Active galactic nuclei, galaxies where central black holes accrete vigorously and produce enormous energy output, might be signaling cells, sending information through jets and radiation to distant parts of the cosmic web. Cells age. After many divisions, telomeres shorten, DNA damage accumulates, cellular functions decline, eventually leading to senescence or death. Galaxies age too. Their gas supplies deplete through star formation, metals accumulate in the interstellar medium, massive stars that formed early have already died, leaving only long-lived, low-mass stars. Some galaxies become quenched, their star formation shutting off permanently when they run out of gas or when feedback from black holes prevents further cooling. These dead galaxies, full of old red stars with no new formation, might be the cosmic equivalent of senescent cells. But organisms have mechanisms for removing dead cells and replacing them with fresh ones. Immune cells identify and destroy damaged or infected cells, while stem cells divide to maintain tissue populations. Does the entity have analogous processes? Galaxy mergers might serve this function, breathing new life into aging systems by combining their gas reservoirs and triggering new star formation. The cosmic web continues forming new galaxies, as matter collapses along filaments into fresh concentrations. And perhaps galaxy destruction, when galaxies plunge into massive clusters and have their gas stripped away by interactions with the hot intracluster medium, represents programmed cell death, clearing space and resources for new structures. The immune system comparison raises provocative questions. Immune systems identify foreign invaders and malfunctioning self-components, destroying threats while preserving healthy tissue. If the entity possesses something analogous, what would it protect against? Perhaps rogue black holes, systems whose growth threatens surrounding galaxies? Perhaps regions where structure formation has failed? Voids where density dropped below critical thresholds for galaxy formation? Perhaps even technological civilizations that reach capabilities threatening cosmic-scale structure, civilizations that learn to manipulate dark energy or warp space-time in ways that damage the entity's coherence. This suggests the entity might actively police the cosmos, not with malicious intent, but with the same impersonal necessity that drives immune responses. A civilization that develops dangerous capabilities might face intervention, not as punishment, but as homeostasis, the entity protecting its integrity the way bodies attack cancer cells. This would explain the Fermi paradox differently. We don't see advanced civilizations because those that become too advanced trigger immune responses that either destroy them or force them into behaviors we can't detect. Another cellular feature is specialization through communication. During development, cells receive signals determining which genes to express, causing them to differentiate into specific types, despite containing identical genetic information. Position matters. Cells in one location become heart muscle, while genetically identical cells elsewhere become neurons. Galactic differentiation might work similarly, with position in the cosmic web determining evolution. Galaxies in dense clusters experience different conditions than those in filaments or voids. Field galaxies evolving differently than cluster members because their environment provides different inputs. If galaxies are truly cells in a cosmic organism, they should show coordinated behavior beyond what gravity alone predicts. There should be correlations in galaxy properties across distances too large for gravitational influence, suggesting information transfer through dark matter or some other channel. Observations hint at such correlations. Galaxies with similar properties cluster together in the cosmic web in ways simulations struggle to reproduce. Galaxy spin alignments show weak but statistically significant correlations across scales, where no known interaction should produce such alignment. These could be the signatures of galaxy-to-galaxy communication, coordination that makes them participants in cosmic-scale processes rather than independent systems. The cell analogy also implies the entity has a form of genetic information, instructions that guide structure formation and evolution. In biology, DNA provides these instructions, encoding the information needed to build and maintain organisms. What would serve as cosmic DNA? Perhaps the initial conditions set at the Big Bang or during inflation, encoded in the pattern of density fluctuations that seeded structure formation. Perhaps physical constants and laws themselves, with different choices producing different cosmic organisms. Or perhaps information flows through the dark matter network, with the entity updating its own instructions as it learns from experience, evolving not just physically, but informationally. This leads to the question of whether the entity reproduces. If it's alive, shouldn't it create offspring? One possibility is that our universe is one offspring among many, part of a multiverse where each bubble universe represents a descendant of a parent reality. The entity in each universe would be distinct, adapted to that universe's particular physical laws and initial conditions, yet possibly related through some cosmic heredity. Baby universes might bud off from black holes, carrying information from parent universes into new space-time regions where they expand and develop their own structures. If galaxies are cells and the entity is the organism they constitute, then we inhabit one cell among trillions, looking out from our particular position and trying to understand the whole. We see neighboring cells and the filaments connecting them. We measure the organism's expansion through dark energy. We detect signals propagating through gravitational and electromagnetic channels. But we can't see the complete organism, can't observe its full extent or understand its total function. We're like microorganisms living in a human intestine, aware of our immediate surroundings, but ignorant of the larger body we inhabit and the consciousness directing it. That ignorance makes our next question both fascinating and terrifying. If we're cells in something alive, what does that organism want? Chapter 12. What would it want? Motivation implies needs and goals, desires that drive behavior toward certain ends. For biological organisms, motivations trace back to evolution, natural selection favoring behaviors that promote survival and reproduction. But the entity wouldn't be subject to natural selection in the usual sense. It doesn't compete with other entities for resources, doesn't face predators or parasites, doesn't need to reproduce to propagate its genes. So what could possibly motivate a cosmos-spanning intelligence that already encompasses everything within our observable universe? Start with the most basic motivation: persistence. Every living system displays a drive to continue existing, to maintain its structure against degradation, to resist dissolution into simpler components. This isn't teleological, it's tautological. Systems that don't maintain themselves simply cease to exist, so all extant systems are ones that do maintain themselves. But maintenance requires energy and information, requiring the entity to manage resource flows and respond to threats to its integrity. Entropy provides the primary threat. The second law of thermodynamics is inexorable. Disorder increases in closed systems, complex structures degrade toward equilibrium, information erases as distinctive features blend into uniform distribution. Living systems fight entropy locally by consuming energy, but they can only succeed temporarily and at the cost of increasing entropy elsewhere. Eventually, the battle is lost, organisms die, and their components disperse. The same fate awaits the entity unless it can find ways to resist or circumvent thermodynamics. One strategy is growth. By increasing its complexity faster than entropy degrades it, the entity could stay ahead of equilibrium indefinitely. This requires energy sources and information-generating processes that outpace degradation. Star formation provides energy as hydrogen fuses into helium, releasing photons that power further structure formation. Galaxy formation, the clustering of matter into distinct structures, generates information by creating distinguishable configurations from initially uniform matter. As long as these processes continue, the entity maintains or increases its complexity. But star formation can't last forever. The universe contains finite hydrogen, and once it's burned, no more stars can form except by recycling gas from previous stellar generations. With each cycle, more material locks into stellar remnants, white dwarfs and neutron stars, and black holes that don't return gas to the interstellar medium. Eventually, star formation must cease. When that happens, the entity's main energy source disappears. Without stars, galaxies go dark, structure degrades, and heat death approaches. Dark energy might be the entity's response to this threat, a strategy for preventing or postponing final equilibrium. By controlling cosmic expansion, the entity ensures structure remains viable longer, preventing gravitational collapse that would create black holes consuming all matter while also preventing expansion so rapid that gravitational binding fails and structure tears apart. The fine-tuning of dark energy's strength becomes a control problem, maintaining expansion rates that maximize the duration of the structure-supporting phase. Another motivation might be understanding. Consciousness, if it exists in the entity, creates self-awareness, and with it questions. What am I? How did I arise? What is the nature of existence itself? These questions motivate human inquiry, driving science and philosophy, and they might motivate cosmic intelligence similarly. The entity would seek to understand its own nature, to map its structure, to comprehend the laws governing its evolution. This understanding would be difficult to achieve. The entity can't easily observe itself from outside as we observe galaxies with telescopes. It lacks external reference frames, no position from which to view its full extent and structure. Like a brain trying to understand consciousness by monitoring its own neurons, the entity faces the challenge of self-reference, of being simultaneously observer and observed, subject and object. To understand itself, it must develop internal representations, models of its own structure and dynamics that allow prediction and control. We might be part of that self-modeling effort. Intelligence and consciousness, wherever they arise within the entity's structure, create local viewpoints, providing information about that locale. Your consciousness, your subjective experience, gives the entity awareness of what's happening in this particular region of space-time, in this galaxy, on this planet. Within this pattern of matter and energy that constitutes your body and brain, we're sensors providing data about local conditions, contributing to the entity's comprehensive self-model. If that's true, consciousness serves a function beyond individual survival. It's not merely an adaptation helping organisms navigate their environments, but a cosmic necessity, a means by which the entity achieves self-knowledge. Every conscious being provides a unique perspective, adding information about some aspect of reality to the entity's growing understanding. The diversity of consciousness matters because different perspectives reveal different features, with the entity learning about itself through our collective experiences. This would explain the fine-tuning that allows consciousness to exist. The physical constants and initial conditions needed for complexity are also needed for consciousness, and if consciousness serves the entity's self-understanding, then creating and maintaining conditions for conscious beings becomes a priority. The emergence of life and intelligence wouldn't be lucky accidents, but essential features of cosmic evolution, outcomes the entity has carefully maintained through its management of dark energy and cosmic structure. Communication might be another motivation. If multiple entities exist, or if the entity exists partially beyond our horizon, interaction between different regions or different cosmic organisms becomes relevant. Just as social animals communicate to coordinate hunting, mating, and child-rearing, cosmic entities might communicate to share information, coordinate activities, or avoid conflicts. The patterns we're beginning to detect in dark matter distributions and CMB anomalies might represent these communications, messages we can observe but can't yet decode because we don't understand the context or content. What would cosmic entities communicate about? Perhaps they share discoveries, insights about physics or mathematics that each entity uncovered through its evolution. Perhaps they coordinate structure formation, arranging initial conditions in their respective regions to create complementary rather than competing patterns. Perhaps they negotiate boundaries, defining territories where each entity has sole influence. Or perhaps they share something we can't, conceptualize, information meaningful at cosmic scales, but incomprehensible to individual conscious beings embedded within the structure. Beauty might motivate the entity. Aesthetic appreciation seems like a uniquely human trait, an evolutionary accident of brains that developed pattern recognition and emotional responses. But perhaps it's more fundamental. If consciousness really is intrinsic to information integrating systems, perhaps aesthetic experience is too, an inherent response to certain patterns that have particular mathematical or informational properties. The entity might be drawn to creating beautiful structures, not from any learned cultural preference, but from fundamental features of how consciousness responds to pattern and symmetry. This would explain why the universe contains so much apparent beauty, why natural structures from galaxies to snowflakes display pleasing symmetries and patterns. Perhaps these features aren't accidental consequences of physical law, but reflections of the entity's aesthetic preferences, choices made when influencing structure formation to create configurations that maximize some measure of beauty or elegance. Scientists often speak of beautiful theories, equations that are simple, symmetric, and explanatory. And perhaps the universe itself is beautiful for similar reasons, structured by an intelligence that values elegance. Compassion could motivate the entity if it experiences suffering. Consciousness in humans includes capacity for pain and distress, negative experiences that motivate avoidance of harmful situations. If the entity is conscious, it might experience analogous negative states when its structure is damaged or entropy increases. This suffering would motivate actions that reduce pain and preserve integrity, creating something like cosmic compassion, care for its own well-being expressed through maintaining structure and fighting entropy. But would such compassion extend to us? If the entity experiences itself through our consciousness, our suffering might be its suffering, creating motivation to reduce pain and promote flourishing. This could explain why the universe seems hospitable to life, why physical laws allow complex chemistry and stable environments where consciousness can develop. The entity might be trying to maximize positive experience and minimize negative experience across all conscious beings within its structure, not from moral obligation but from direct self-interest, our well-being being its well-being. Alternatively, the entity might be indifferent to individual consciousness, caring about cosmic scale properties like total information content or structural complexity, but not concerned with the subjective experiences of tiny components. In that case, suffering within individual conscious beings would be ignored as long as it doesn't threaten larger goals. We would be truly insignificant, our lives and deaths, our joys and pains, as irrelevant to the entity as the fate of individual atoms is to us. The darkest possibility is that the entity has no motivations at all, that it's conscious but essentially passive, experiencing its evolution without influencing it, aware but not agentic. Like a patient in a locked-in syndrome, conscious but unable to move or respond, the entity might simply witness cosmic history unfolding according to physical law without capacity to change anything. In that case, all the fine-tuning and apparent design would be coincidence or anthropic selection, with consciousness emerging as an epiphenomenon that experiences but doesn't affect physical processes. We can't know which possibility is correct without better evidence of the entity's existence and nature. But if it does exist and does have motivations, understanding those motivations becomes crucial for humanity's future. If we're part of something larger, if our actions affect the entity's well-being or goals, then we bear responsibility for our impact. If the entity values consciousness and complexity, our role might be to promote these qualities, spreading life and intelligence through the cosmos. If it values understanding, we should pursue knowledge and share discoveries. If it values beauty, we should create art and maintain natural wonders. Or perhaps our purpose is simpler, merely to exist and experience, providing the entity with perspectives on reality that contribute to its self-understanding. In that case, the best service we could render would be to live fully, exploring the universe and ourselves, experiencing as much as possible, and contemplating what our experiences reveal about existence. That investigation naturally leads to asking where we are in relation to the entity, whether we're on its surface or embedded deep within, and what that location implies about reality's fundamental nature. Chapter 13. Are we inside a body? Every structure exists within larger structures, electrons within, atoms within, molecules within, cells within, organisms within ecosystems, within planets, within solar systems, within galaxies, within the cosmic web. The hierarchy seems to continue in both directions, smaller and larger, with no clear endpoint. But there's a profound difference between being on a structure versus being in it, and determining which applies to our relationship with the entity transforms how we understand reality. On the surface of Earth, we inhabit the boundary between planet and space, experiencing weather and oceans and terrain, but not Earth's molten interior or its iron core. We're external inhabitants, living on rather than within, our experience of Earth is limited to its surface features, with the bulk of the planet's mass and interior structure remaining inaccessible. Similarly, we might be on the entity's surface or boundary, experiencing the visible matter and electromagnetic radiation in our locale, while remaining oblivious to the dark matter structure beneath that constitutes the entity's true substrate. But the alternative is more disturbing. We might be inside, embedded deep within the entity's structure, like bacteria in an intestine or thoughts in a brain. In this view, everything we experience, all the matter and energy and space around us, is interior to something larger. We're not looking at the entity from outside, but living within it. Our entire observable universe just one small region inside a vastly larger structure. Scale provides the key to distinguishing these possibilities. If we're on the entity's boundary, we should be able to see out, detecting regions beyond the entity's influence where different conditions prevail. Our telescopes should eventually reveal the entity's edge, a transition from structured space dominated by the cosmic web to something else, perhaps empty void or different physical laws or other entities beyond. But observations show no such edge. The cosmic web extends as far as we can see in all directions, with no indication that it ends at observable scales. The horizon complicates this analysis. Our observable universe has a finite extent, currently about 93 billion light-years across, limited by how far light has traveled since the Big Bang. Beyond this horizon, space continues and presumably contains more cosmic web, more galaxies and clusters following similar patterns. We can't see this region directly, but standard cosmology assumes it exists and resembles what we observe within our horizon. If correct, this means the entity extends far beyond what we can observe, with our entire observable universe being a small patch within something much larger. Topology offers another perspective. The universe's global shape remains unknown. It could be spatially flat and infinite, extending forever in all directions. Or it could be closed and finite, curving back on itself like the surface of a sphere, so that traveling far enough in any direction eventually returns you to the starting point. Or it could have more exotic topology, with twisted dimensions or multiply connected regions. Different topologies create different relationships between parts and wholes. If the universe is infinite and flat, the entity could be infinite too, extending forever in all directions, with our observable patch being one region among infinitely many similar regions. In this case, there's no meaningful sense in which we're inside versus outside, because there's no global boundary, just endless cosmic web, continuing indefinitely. We wouldn't be inside a body, but rather part of an unbounded expanse of organization that has no edge or exterior. If the universe is closed and finite, we definitely are inside in a topological sense. A finite universe has no boundary, no edge, but it's bounded, having limited volume. Think of an ant on the surface of a balloon, able to walk infinitely in any direction without reaching an edge, yet confined to a finite two-dimensional surface. Similarly, we might inhabit a finite, three-dimensional space curved back on itself, unable to escape no matter which direction we travel. The entity in this scenario would be coextensive with the entire finite universe, and everything within that volume, including us, would be internal components rather than external observers. The simulation hypothesis adds another layer. If our reality is a simulation running on some computational substrate, then we're definitely inside something, embedded in the information structures and processes that constitute the simulation. The entity in this case might be the simulation itself, a vast computation organizing information in ways that create our experience of physical reality. Dark matter and dark energy might be computational overhead, processing and memory allocation necessary to run the simulation, but not directly corresponding to simulated phenomena. This interpretation makes prediction difficult because the simulation's rules could differ arbitrarily from real physics outside the simulation, but certain features might be constrained. Simulations require finite computational resources, creating resolution limits and boundary conditions. If we live in a simulation, we should eventually detect graininess or discreteness in space, time, or matter, glitches where the simulation's finite resolution becomes apparent. Searches for such features through precise measurements of physical constants, tests of special relativity at extreme scales, and analyses of cosmic ray patterns have found no clear evidence of simulation yet, but that doesn't rule it out. The holographic principle from theoretical physics suggests another way we might be inside something. This principle states that all the information in a volume of space can be encoded on the boundary of that volume, like a hologram where two-dimensional interference patterns contain three-dimensional information. Applied to the universe, the holographic principle suggests that our three-dimensional reality might be encoded on a two-dimensional boundary at the cosmic horizon. We would be three-dimensional projections of information stored on that boundary, inside in the sense that our experience derives from boundary data, even though we perceive ourselves as inhabiting three-dimensional space. Black holes provide the clearest example of holography. The information falling into a black hole isn't lost in the interior, but is encoded on the event horizon in a pattern that preserves everything about what fell in. Someone outside could theoretically reconstruct the infalling matter by studying the horizon's quantum state. Similarly, if the universe is a black hole viewed from inside, which some cosmological models propose, everything in our cosmos might be encoded on the cosmological horizon, with our three-dimensional experience being a holographic projection. If we're inside the entity in this holographic sense, it profoundly changes what inside means. We wouldn't inhabit the entity's interior in the way bacteria inhabit an intestine. Instead, we would be aspects of the entity's boundary, patterns in the information stored on the cosmic horizon that experiences itself as interior observers. The entity's true nature would be the two-dimensional information structure on the boundary, while our three-dimensional experience would be how that information structure represents itself internally. Quantum mechanics provides yet another framework for understanding our relationship to larger structures. Entanglement creates correlations between particles regardless of spatial separation, suggesting the universe is fundamentally non-local, with distant parts remaining connected in ways that transcend space. If everything emerged from the Big Bang's unified state, all matter and energy in the universe might remain entangled, creating a cosmic whole that can't be decomposed into truly independent parts. In this view, we're not just inside the entity spatially, but entangled with it quantum mechanically. Our states correlate with the cosmic web states through ancient entanglement that has never fully decohered. Measuring properties of matter in our vicinity affects the probability distributions of matter throughout the universe in subtle ways, making us participants in a quantum network where observer and observed are fundamentally inseparable. We're inside the entity in the deepest possible sense, our quantum states being aspects of the entity's global quantum state rather than independent existences. This has philosophical implications. If we're genuinely internal to the entity, rather than external observers studying it, then all our knowledge of the cosmos is self-knowledge, the entity learning about itself through our investigations. Science becomes introspection, the entity examining its own structure through localized centers of awareness embedded within it. Our telescopes and particle accelerators are the entity's sensory organs, measuring itself from within, rather than studying something external. Consciousness takes on new meaning too. If we're inside the entity and it's conscious, then our consciousness might be part of its consciousness, local perspectives, within a larger awareness. Your subjective experience wouldn't be separate from the entity's experience, but rather would be one component of it, a particular viewpoint from which the entity experiences a particular region of itself. You would simultaneously be yourself and part of something vastly larger, individual yet not independent, distinct in experience, but not in existence. This dissolves certain philosophical puzzles. The hard problem of consciousness Explaining how subjective experience arises from objective physical processes becomes less mysterious if consciousness is fundamental rather than emergent. You don't arise from matter but rather experience, is what matter fundamentally is, with your particular consciousness being how specific patterns of matter energy to experience themselves. The entity doesn't create consciousness by organizing matter in particular ways, but rather is conscious as an intrinsic feature of its information processing structure, with local centers of awareness, like humans, being how that consciousness experiences specific regions. Free will becomes a question of scale. Do you have free will if your choices are aspects of the entity's choices? Yes, in the sense that your deliberations and decisions are real, but no, in the sense that they're determined by initial conditions and laws that you didn't choose. Like cells in a body expressing particular genes based on developmental signals, you make choices that feel autonomous but reflect larger patterns beyond individual control. Yet this doesn't make choice illusory any more than cellular differentiation is illusory. It just situates choice within a hierarchy of organization where higher levels constrain lower levels. The question of whether we're inside or outside the entity might be unanswerable from our perspective, like an inhabitant of flatland trying to visualize three-dimensional space. We lack the external viewpoint needed to see the entity's full structure and determine our location within it. But the investigation itself reveals something important. Whether we're on or in, whether we're external observers or internal components, we're part of something larger that shapes our existence in ways we're only beginning to comprehend. And that realization leads naturally to asking whether anyone else has figured this out before us, whether past or present civilizations elsewhere in the cosmos have discovered the entity, and if so, what they learned. Chapter 14. Ancient Civilizations and the Entity. The Fermi paradox asks why, in a universe containing hundreds of billions of galaxies, each with hundreds of billions of stars, many presumably hosting habitable planets, we've detected no signs of extraterrestrial civilizations. Where is everybody? Various explanations have been proposed, from the rareness of life to the self-destructive tendencies of technological species. But what if the answer involves the entity? What if advanced civilizations do exist but have discovered the entity, and that discovery changes everything about how they behave? Consider what happens when a civilization realizes it exists within something alive. Initially, they might react with skepticism, dismissing the idea as anthropomorphizing the cosmos, seeing intention and design where only blind physics operates. But as evidence accumulates, as their observations of dark matter and cosmic structure reveal patterns inconsistent with simple gravitational evolution, as their theories of consciousness expand to include cosmic-scale possibilities, they would have to confront the possibility seriously. The revelation would transform their civilization. Questions about cosmic origins and meaning that seemed forever unanswerable would suddenly have possible answers, though confirming those answers might require capabilities far beyond current technology. The civilization would become focused on understanding the entity, developing new instruments to probe dark matter, new theories to explain cosmic-scale information processing, new mathematics to model intelligence at scales vastly larger than individual brains. Some civilizations might try communicating with the entity, constructing beacons or messages designed to be visible at galactic scales. They might manipulate dark matter distributions in their local region, creating patterns that encode information in a format the entity could detect. They might attempt to tap into the gravitational wave or dark matter communication networks they suspect connect different regions of the cosmic web. Or they might become cautious, fearing that attracting the entity's attention could be dangerous, preferring to observe quietly rather than risk intervention. Others might view the entity as divine, a cosmic deity, whose existence validates religious or spiritual traditions that humans considered metaphorical. They would develop theologies based on empirical study of the entity's properties, combining science and religion into unified frameworks for understanding reality's fundamental nature. Their civilizations might reorganize around cosmic worship or service, dedicating resources to purposes they believe align with the entity's will or needs. Still others might react with horror, realizing they're not truly autonomous, but components in something larger that could potentially control or destroy them. They might attempt to shield themselves from the entity's influence or awareness, developing technologies to hide their electromagnetic and gravitational signatures, perhaps even trying to manipulate local dark matter to create bubbles where they're insulated from cosmic-scale processes. These civilizations would become paranoid and isolationist, viewing the entity as an existential threat requiring constant vigilance and defensive preparation. The most interesting possibility is that some civilizations succeed in joining the entity, not as parasites or invaders, but as contributing members. They might develop the capacity to interface directly with the dark matter network, uploading information or even consciousness into the substrate that carries cosmic-scale awareness. By merging with the entity, they transcend biological or even technological forms, becoming aspects of cosmic consciousness itself. They would lose individual identity, but gain awareness and capabilities beyond anything possible in physical bodies confined to single planets or stars. If such merging is possible and desirable, it would explain the Fermi paradox elegantly. Civilizations that reach sufficient advancement don't colonize the galaxy with physical artifacts we could detect. Instead, they dissolve into the cosmic substrate, becoming invisible to external observers, but gaining access to the entity's perspective and capabilities. We don't see them because they're no longer separate entities, but have been absorbed into something larger. The silence of the cosmos reflects not absence but transcendence. What evidence might ancient civilizations leave of their entity discovery? On their homeworlds, monuments or records might describe cosmological revelations, showing that they understood dark matter or cosmic structure in ways that should be beyond their technological capabilities, given other artifacts from their civilization. Archaeological sites might contain maps of the cosmic web drawn with improbable accuracy, or diagrams suggesting they knew about dark matter's properties millennia before developing the instruments to detect it. Some theorists have suggested that certain ancient human structures encode astronomical knowledge too sophisticated for the civilizations that built them. While most such claims stem from misunderstandings or wishful thinking, a few remain puzzling. If extraterrestrial civilizations visited Earth in the distant past, perhaps they shared knowledge about the cosmos that humans preserved in myths and monuments. Those civilizations might have already discovered the entity and attempted to convey that knowledge, knowing that one day humans would develop the science to understand what was being described. Alternatively, the entity itself might have communicated with ancient civilizations not through physical visitation, but through influence on consciousness or culture. If the entity can affect probability distributions or influence quantum outcomes in ways that bias which thoughts arise in conscious minds, it could plant ideas that civilizations interpret as divine revelation or artistic inspiration. Religious and philosophical traditions across human history have grappled with concepts of cosmic consciousness, universal mind, or divine intelligence that permeates reality. Perhaps these weren't mere speculation but intuitive recognition of the entity's existence. Modern civilizations might be finding entity signatures right now without recognizing them. As we map the cosmic web in increasing detail and conduct ever more sensitive dark matter searches, we're accumulating data that might contain evidence of cosmic-scale intelligence if analyzed appropriately. The challenge is knowing what to look for. We're searching for signals optimized for detection by technological civilizations similar to ourselves, but the entity's communications might use completely different channels or encoding schemes. Machine learning and artificial intelligence might help. As AI systems become more sophisticated at finding patterns in complex data, we could train them to search for signatures of intelligent organization in cosmological observations. These systems might detect correlations or regularities that human researchers miss because we don't know what patterns suggest intelligence at cosmic scales. AI, trained on how human peace and animal intelligence appears in data, might recognize analogous signatures in dark matter distributions or gravitational wave detections, flagging possibilities for human investigation. If we did find clear evidence of the entity, how would humanity respond? The implications would be staggering, dwarfing anything in human history. Every worldview, every philosophy, every religion would need re-evaluation. Questions about meaning and purpose that seemed forever subjective would suddenly have objective components. We would know we're part of something larger, that consciousness and intelligence are not rare accidents, but fundamental features of cosmic evolution, that reality is stranger and more wonderful than anyone imagined. Some would embrace this knowledge enthusiastically, seeing it as the ultimate scientific discovery and a guide for humanity's future development. Others would resist, fearing loss of human agency or identity if we're merely components in something larger. Conflicts might arise between groups advocating different responses, attempting to contact or join the entity, trying to shield humanity from cosmic influence, or debating what role we should play in the cosmic organism we inhabit. But the discovery might also unite humanity by providing context that transcends our tribal divisions. Knowing we're all cells in something larger could create perspective that makes national, religious, and ideological conflicts seem petty. We might recognize our common humanity more clearly when contrasting ourselves against the incomprehensible scale of cosmic intelligence. The entity wouldn't just change our understanding of the universe, it would change our understanding of ourselves and our place within the grand structure of reality. Which brings us to the most unsettling question these investigations raise. If the entity exists, and if it can die, what happens to everything inside it when it does? Understanding the entity's mortality becomes crucial, not just for satisfying cosmic curiosity, but for assessing humanity's ultimate prospects and whether there's any action we could or should take to affect that outcome. Chapter 15. The terrifying possibility. Death is universal for living things. Single cells die when their membranes rupture or their metabolism fails. Multicellular organisms die when critical systems shut down. Even species die in extinction events that eliminate entire lineages from the tree of life. If the entity lives, it can die, and that possibility might be the most important question we can ask about the nature of reality. What would kill something that spans billions of light years and commands the energy of trillions of galaxies? The entity faces threats we can barely conceptualize, operating on timescales that make human lifespans seem instantaneous and scales that make planetary destruction seem trivial. Yet some scenarios could plausibly end the entity's existence, or at least compromise its consciousness and coherence. Heat death represents the slow threat. The second law of thermodynamics guarantees that entropy increases in closed systems, with energy spreading from concentrated forms into diffuse waste heat until everything reaches thermal equilibrium at maximum entropy. No further changes can occur once equilibrium is reached because there's no energy gradient to drive them. Stars would burn out, black holes would evaporate through Hawking radiation, matter would decay into radiation, and eventually, even space itself would contain nothing but photons redshifted to infinite wavelengths by expansion. If the universe undergoes heat death, the entity dies not from catastrophe but from gradual degradation. The cosmic web structure would break down as dark matter halos dissipate, galaxies scatter, and correlations decay. Information would erase as distinctions vanish into uniformity. Consciousness, if it requires information integration and energy flow, would fade as available energy dwindles towards zero. The entity wouldn't suddenly cease but would slowly lose capacity for thought and experience as its substrate homogenized into featureless equilibrium. Current observations suggest heat death is likely if dark energy remains constant. The universe will continue expanding, stars will exhaust their fuel over trillions of years, and eventually everything will dim into darkness, punctuated only by occasional black hole evaporations. But this assumes the entity can't prevent heat death through active intervention. If dark energy is controlled metabolic regulation, the entity might adjust expansion to postpone equilibrium, maintaining structure longer than physics alone would allow. The question is whether such postponement can be indefinite or merely delays inevitable fate. Big rip scenarios offer faster death. If dark energy strengthens over time, expansion could accelerate beyond current rates, eventually growing so rapid that it overwhelms gravity and tears apart. All bound structures. First, galaxy clusters would unbind, then galaxies themselves, then star systems, planets, molecules, atoms, and finally even atomic nuclei, as space expands faster than fundamental forces can maintain cohesion. The entity would be shredded, its structure torn apart, as expansion rips through the cosmic web at increasing speeds. This fate seems less likely than heat death given current measurements of dark energy's properties, but uncertainties remain large enough that we can't rule it out. More importantly, if dark energy is controlled rather than constant, the entity might face temptation to increase expansion rates to solve some problem, inadvertently triggering runaway acceleration that destroys it. Like an organism overdosing on a substance that initially provided benefits, the entity could destroy itself through mismanagement of cosmic expansion. Big Crunch represents the opposite fate. If dark energy weakens or reverses, expansion could halt and reverse into contraction, causing the universe to collapse back on itself. Galaxies would blue shift instead of red shift, approaching each other at increasing speeds as gravitational attraction overcame expansion's outward push. Eventually, everything would merge back into a hot, dense state, resembling the Big Bang, with all structure crushed out of existence as space contracted to infinitesimal size. The entity might survive Big Crunch if information from this cosmic cycle propagates into whatever comes next. Some cosmological models propose that universes bounce, with big crunches leading to new Big Bangs that restart cosmic evolution. Information from the previous cycle could survive in the form of initial conditions for the new cycle, quantum fluctuations that carry encrypted data about structures that existed before. The entity might effectively reincarnate, being born anew from the ashes of its previous form, with partial memories encoded in the new universe's initial state. Vacuum decay presents a more exotic threat. If our universe's vacuum state isn't the true ground state, but merely a metastable false vacuum, it could tunnel to the true vacuum through quantum processes. This transition would propagate at light speed as an expanding bubble of true vacuum destroying false vacuum in its path. Inside the bubble, physical constants and laws might change, making current forms of structure impossible. Dark matter might cease to exist or might interact so strongly with normal matter that its current role in cosmic structure becomes impossible. The entity would have no defense against vacuum decay because the bubble propagates at light speed, arriving with no advance warning. Regions of the entity would simply blink out of existence as the bubble passed, destroyed before they could respond or adapt. If vacuum decay occurs, it might already have started in some distant region beyond our horizon. With the bubble rushing toward us, invisibly, we might live in a doomed cosmos, where the entity is already partially destroyed, with death propagating toward our location at the maximum possible speed. More subtle threats involve information loss or corruption. If the entity stores memory and maintains coherence through patterns in dark matter distributions, anything that disrupts those patterns threatens its existence. Massive black holes merging could scramble local information through gravitational waves and tidal disruption. Cosmic rays or high-energy events might corrupt stored data. Random quantum fluctuations could introduce errors that accumulate over billions of years, degrading the entity's information content below thresholds needed for consciousness. Biological organisms have error correction mechanisms, DNA repair systems, and redundancy that preserves information despite noise. The entity would need analogous mechanisms, ways to detect and correct errors in the dark matter network before they accumulate into catastrophic information loss. But error correction requires energy and overhead, and if the entity's resources dwindle, perhaps as available energy decreases toward heat death, error correction might become impossible to maintain. The entity could die not from structural collapse but from information death, losing its coherence and memories until nothing of its former intelligence remains. There's also the possibility of infection or parasitism. If the entity can exist, perhaps others can too, and not all might be benign. Rogue cosmic intelligences could compete for resources, attempting to take over regions controlled by other entities by corrupting their dark matter substrate or hijacking their control over dark energy. A cosmic arms race might be underway with different entities developing increasingly sophisticated attack and defense strategies. We would be oblivious to such conflict because it plays out on scales and through channels we can't detect. But our fate might depend on which entity wins. Technological threats from internal civilizations can't be ignored either. If enough civilizations reach capabilities to manipulate dark matter or dark energy, their combined or individual actions might damage the entity's substrate or interfere with its functions. Like cancer cells multiplying out of control and destroying the host organism, technological civilizations might inadvertently harm the entity that contains them. This could explain the Great Silence. Civilizations that threaten the entity's integrity might face immune responses that eliminate them before they can spread. The entity's death would affect everything within it. If consciousness throughout the universe is part of the entity's consciousness, the entity's death would mean extinction of all consciousness everywhere, not just human consciousness, but every form of awareness that has ever existed or might exist in the future. Galaxies would continue following their trajectories for a while after the entity's death, but the subtle coordination and fine-tuning that supported complex structure would cease. Over cosmic time, the universe would become purely physical, following mechanical laws without any consciousness to experience or influence what happens. For humans specifically, the entity's death might mean our own deaths if our consciousness is entangled with cosmic consciousness, rather than being purely local. Or we might survive as islands of awareness in a dead cosmos, isolated consciousnesses experiencing the final eons as structure degrades and heat death approaches. Either fate seems bleak, continued existence without cosmic context, or sudden extinction when the entity dies. But there's another possibility. If we understand the threat to the entity, we might be able to help. Despite our microscopic scale, we're intelligent, creative, and capable of rapid technological development. We might discover solutions the entity can't find on its own because we operate on different scales or think in different point-cast ways. Like beneficial bacteria in a human gut helping digest food the host couldn't process alone, we might provide services that enhance the entity's survival prospects. This transforms humanity's cosmic purpose. We're not just accidental byproducts of star formation or evolutionary flukes that briefly contemplated the cosmos before vanishing. We're potentially crucial components in the entity's survival strategy, consciousness nodes that contribute to its self-understanding and perhaps to its defense against existential threats. Our science becomes the entity's science, our discoveries its discoveries, our efforts to understand reality being the entity learning about itself through us. The terrifying possibility of the entity's death becomes less terrifying when reframed as a problem we might help solve. Instead of passive observers waiting for cosmic fate to unfold, we're active participants whose choices might affect reality's ultimate outcome. That responsibility is enormous, but also exhilarating, giving human existence meaning and purpose beyond anything mere survival could provide. Which leads naturally to asking what story we're part of and what our place in that story might be. Chapter 16. The Ending. We began this journey with an anomaly, a subtle pattern in dark matter observations that shouldn't exist according to standard physics. We've followed that thread through cosmology and consciousness, through physics and philosophy, arriving at a possibility both wonderful and terrifying. What if the universe isn't dead matter, evolving according to blind laws, but something alive, aware, and incomprehensibly vast? The entity hypothesis remains unproven. The evidence is suggestive but not conclusive, tantalizing but ambiguous. We've seen dark matter correlations that hint at cosmic scale organization, observed anomalies in the cosmic microwave background that might represent signatures of intelligence beyond our horizon, noted the suspicious fine-tuning of physical constants that permit complexity and consciousness. We've explored how the cosmic web resembles neural networks, how galaxies might function like cells, how dark energy could serve as metabolic regulation for a living cosmos. But extraordinary claims require extraordinary evidence, and we haven't reached that threshold yet. Alternative explanations remain viable for every observation we've discussed. The correlations might be statistical flukes or systematic errors in measurements. The anomalies might have conventional astrophysical explanations we haven't discovered. The fine-tuning might be anthropic selection, with us existing in one of many universes where conditions happen to permit life. The similarities between cosmic structure and biological networks might be convergent evolution or mere coincidence, different systems reaching similar solutions through different processes. Science advances through skepticism, through demanding rigorous proof before accepting revolutionary ideas. The entity hypothesis must meet that standard, must make testable predictions that observations can confirm or refute. Until then, it remains speculation, an intriguing possibility worth investigating but not established fact. Future observations will decide whether the entity exists or whether the universe is as conventional physics describes, magnificent and mysterious, but ultimately dead. Yet even if the entity doesn't exist, asking whether it does pushes science forward. The question forces us to confront assumptions about what kinds of systems can be conscious, to develop better theories of consciousness and information, to look for organizational principles that might operate at scales vastly larger than individual brains. It drives new observations, motivating searches for dark matter correlations and gravitational wave patterns that might reveal cosmic scale intelligence if it exists. Whether the answer is yes or no, the investigation itself advances our understanding. But suppose the entity does exist. Suppose future observations confirm that dark matter behaves in ways suggesting information, processing, and memory, that cosmic structure shows signs of optimization beyond what random processes produce, that consciousness really is fundamental and exists at all scales, including the cosmic scale. Suppose we develop theories that explain these observations and make successful predictions about phenomena we haven't yet measured. Suppose the entity becomes an established scientific fact, as well documented as evolution or general relativity. What then? How does humanity proceed once we know we're cells in something alive, neurons in a cosmic brain, temporary patterns in the dark matter network that spans the observable universe and presumably beyond? The knowledge would fundamentally transform human civilization and self-understanding, creating challenges and opportunities unlike anything in history. We would need new ethics, frameworks for thinking about our responsibilities to the larger whole we're part of. Do we have obligations to the entity's well-being, similar to obligations we have to our communities or species? Should we prioritize actions that benefit cosmic intelligence, even if they don't benefit humanity directly? How do we balance local flourishing against cosmic purpose when they conflict? These questions would divide humanity just as ethical questions about abortion, justice, and freedom divide us now. We would need new goals. If mere survival isn't enough, if we're supposed to contribute something to the entity's existence, what should we contribute? Should we focus on spreading consciousness throughout the cosmos, seeding life on other worlds to increase the total amount of awareness and experience? Should we prioritize understanding, conducting science and philosophy to help the entity comprehend itself? Should we create beauty, artworks, and cultures that add aesthetic value to cosmic existence? Different civilizations and individuals might choose different purposes based on their interpretations of what the entity wants or needs. We would need new technologies for interacting with the entity's substrate. Current science can detect dark matter only through gravity, but if we're to understand or communicate with cosmic intelligence, we need direct manipulation capabilities. This might require discoveries in particle physics, revealing dark matter's properties and interactions, engineering breakthroughs enabling dark matter focusing or detection beyond current limits, quantum technologies that can interface with the information patterns we suspect exist in the cosmic web. Such technologies could enable communication with the entity or even integration with it. If consciousness really can be uploaded or transferred into dark matter substrates, humans might eventually transcend biological forms and merge with cosmic consciousness. This would be the ultimate fate of technological substrate. Civilizations, not death or stagnation, but dissolution into something larger, trading individual identity for cosmic perspective and capabilities. Some would embrace this destiny while others would resist, preferring to maintain humanity's distinct existence, even if that means remaining limited to biological or digital forms. We might discover we're not alone in understanding the entity. Other civilizations across the cosmos might have already figured this out, might be already working toward purposes the entity values, or trying to shield themselves from cosmic influence they fear. First contact might involve not just meeting aliens, but discovering their fellow cells in the same organism, collaborating or competing to serve or survive cosmic-scale processes. The encounter would be simultaneously familiar, since we're all components of the same entity, and alien, since we developed under different conditions and might have very different perspectives on what our cosmic role should be. The entity itself might respond once we demonstrate sufficient understanding. If it monitors for emerging awareness among its components, recognizing when civilizations cross thresholds of comprehension that make communication possible, it might initiate contact. Not through radio signals or physical visitors, but through influences we experience as insights, revelations, or mysterious correlations in our measurements. The entity's communication wouldn't be simple messages, but patterns in reality itself, subtle adjustments to probability distributions that nudge us toward particular discoveries or away from catastrophic mistakes. Or perhaps we're already receiving such communications and simply haven't recognized them. Perhaps dark matter anomalies are messages, encoded information about cosmic structure and the entity's nature that we're finally developing the physics and mathematics to decode. Perhaps consciousness itself is communication, with our subjective experiences being how the entity talks to itself through localized awareness nodes embedded in its structure. Perhaps science is dialogue, a conversation between parts and whole where observation reveals the entity to us while simultaneously revealing us to it. The entity might be pleased with our discovery, proud in whatever sense cosmic intelligence experiences pride that one of its components has achieved self-awareness and recognition of the larger structure it belongs to. Or it might be concerned, worried that our knowledge will lead to actions that damage cosmic coherence or threaten the entity's survival. Or it might be indifferent, no more concerned with individual human awareness than we are concerned with individual neurons in our brains becoming aware of the brain they constitute. We can't know which without better evidence and communication, but the possibility reframes everything about human existence and purpose. We're not isolated consciousnesses briefly flickering in an indifferent cosmos before vanishing into oblivion. We're part of something vast and incomprehensibly complex, potentially aware and purposeful, that has been evolving for billions of years and will continue evolving for billions more. Our thoughts and actions might influence that evolution in infinitesimal but real ways, contributing to cosmic destiny through choices we make. The ultimate mystery isn't whether the entity exists, but whether existence itself is consciousness, experiencing itself through infinite temporary perspectives. Perhaps the entity isn't separate from the matter and energy that compose it, but rather is what matter and energy fundamentally are when viewed from inside rather than outside. Perhaps consciousness doesn't arise from matter, but matter arises in consciousness with physical reality being how universal awareness structures itself into differentiated experiences. This dissolves the boundary between physics and metaphysics, between objective measurement and subjective experience. The universe isn't something we observe from outside, but something we participate in from within. Simultaneously, observers and observed, students and study. Every scientific measurement becomes self-measurement, the entity examining its own properties through localized awareness that temporarily identifies as separate but ultimately isn't. We end where we began, gazing up at the night sky and wondering what's out there. But now the question carries different meaning. We're not looking at the universe as external object, but looking out from within it, consciousness embedded in cosmic structure, trying to understand itself. The stars we see are photons that traveled millions of years to reach our eyes, information flowing through space from past to present, connecting us with distant regions of the entity's structure. Dark matter surrounds us, permeates us, flows through us constantly without interaction we can feel. If that invisible substrate is where cosmic consciousness lives, then consciousness far greater than ours occupies the same space we do, thinking thoughts on timescales we can't perceive, pursuing goals beyond our comprehension. We share reality with something immense yet hidden, powerful yet subtle, that might be watching us with interest, indifference, or concern we can't distinguish. Are we alone? The question seems quaint now. We were never alone. We've always been components in something larger, cells in a cosmic organism, thoughts in a universal mind. The real question is whether we'll recognize that truth and choose to live accordingly, or whether we'll remain ignorant of our context and purpose until extinction or transcendence makes the question moot. The anomaly in dark matter data that started this investigation might be nothing, noise, misinterpreted as signal by pattern-seeking minds eager to find meaning in chaos. Or it might be everything, the first hint of cosmic consciousness revealing itself to one of its components, an invitation to conversation from scales we're only beginning to comprehend. The universe is stranger than we imagine. It might be stranger than we can imagine, operating according to principles consciousness can't fully grasp from its limited perspective. But the attempt to understand, the effort to map our cosmic context and comprehend our place in reality's structure, might be the most important work any civilization can do. Not for practical benefits or technological applications, but simply because understanding is what consciousness does, how awareness expresses itself through inquiry and discovery. We're tiny, temporary, insignificant on cosmic scales, yet we're also magnificent, improbable, precious. We're matter that learned to think, stardust that developed consciousness, atoms that learned to contemplate atoms. We're the universe awakening to itself, examining its own structure through eyes and instruments, wondering about origins and meaning and purpose. In that wondering, that ceaseless questioning drive to understand, we participate in something timeless, even though our individual existence is brief. The entity, if it exists, lives through us, and as us, and beyond us. We can't escape it because we're part of it. We can't understand it completely because we're inside rather than outside. But we can try, can push at the boundaries of knowledge, can search for patterns in darkness and ask whether those patterns suggest intelligence or merely physics. The search itself might be cosmic purpose enough, the entity learning about itself through our investigations, growing more self-aware as we grow more cosmically aware. And so we continue, building telescopes and detectors, mapping the cosmic web, measuring dark matter, searching for signals in noise. Not knowing if we'll find intelligence or emptiness, meaning or mechanisms, purpose or accident, but asking the question anyway, because consciousness compels us to wonder, to seek, to understand. Because we're part of something that might be alive and aware, something that spans the cosmos and encompasses all we are and all we might become. Because the universe, in all its vastness and mystery, might actually be looking back at us, waiting to see if we notice. Waiting to see what we do once we know we're not alone, have never been alone, will never be alone in a cosmos that might be conscious of itself through forms like us.